other graphs. And also some other services utilize the data, for example, Marine Finland. And here is some example of how the time series look in the map viewer part, so the part which is open for everyone. And here I have an example of the station side. Just select the time series part and then click there and you get the time series of that station. So the blue lines are Earth observation surface temperature data and the red dots are monitoring stations data. These are good examples because there are lots of monitoring station data, but every station doesn't have that much. And in Takka's analysis part, it allows data mining and visualization of this statistical data. There is EO data from the status database, but also the monitoring station data. And the user can define the dashboards, so what they want to see and look, what interests them. And the first application was this Water Framework Directive classification last year. And it's also linked to Syke's water management system called Pisara. And the professional use is quite extensive with regard to status assessments. And this analysis part is scalable for many purposes, and in the future we will take it for other purposes also. Currently it is for signed-in users. And here's just a short demo in the analysis part. So you can select the data sources. Here is some water quality parameters. Then you can select the region you want to see, and then you can select the template. I have selected this classification template. And then you can see that there's the data for many year ranges, and this is the latest year range which I have here. And the results are in the pie charts, bar charts, or tables, or time series. So you can compare between Earth observation and in situ data in yearly data or through all the year range. And you can also get histogram regions, histogram of this region. And also you can get this table summary of the both data sets, so Earth observation and in situ data set. You can look, do they give different kind of answers, results. And there are many more functionalities in this analysis part, not just this one. Also we have the classification team for supporting this classification, and there's in situ data calculated as a statistics for every region like these lakes here. And in gallery part we have image time series of lakes and coastal zones, so 82 lakes and coastal zones 13. And last year we had new functionalities and new filters and so on added to it. So currently there's only true color data in this gallery section, but in the future user can select other data sets and other regions more freely. And here a quick week of one of the blue-green algae monitoring theme, which has been used during Syke's weekly algae reviews during summer. And there is images and also time series of the blue-green algae situations on the Baltic Sea. Takka's usage has been quite extensive. As you see, it has been growing every year. We have average user account over 350 daily. In winter, springtime, over 1,000, and summer a little less. And here these peaks comes from ice cover peaks, ice cover situations, and these other peaks smaller from algae bloom season, summertime. In the newspaper, when there is satellite data concerning our data, we see them also as peaks in our usage. And what's coming up in Takka this year? So we have planned a lot. We will have more teams for many data sets, which will support more on projects and project data. And also functionalities to find relevant data. The gallery will develop more, as I said. There will be a possibility to have this. I have on the right example of seasonal aggregates, so you can have image gallery of, for example, of them. And then also more tools to help finding data, as we have a lot of data in Takka. And more Earth observation data, and more citizen observation data, and more model data. Thank you. And here is people who are having presentation today, so you can go and see and ask more. Thank you.
Okay, so thank you, Hanna. Any questions from the audience?
Thank you for a very nice presentation. I have a question with regard to color of lakes. You were discussing color of lakes, saying that it's true. Color
of lakes.
Yeah, it depends on geometry of observations. So incidence angle, observation angle, if you will change them, color will change, even so lake is essentially the same. So I'm wondering, do you account for this? Is it possible, for instance, to measure the same lake within very short time at different geometries?
I don't myself do these algorithms, so if maybe anyone wants to answer more about the algorithms.
Perhaps it is not the main part of the interface development where Hanna is the specialist, but what we do is we optimize the visualization of the true color images. So what Hanna was explaining was that you can follow the lakes as a series of true color images. So if you want to go in details with radiometric measurements, then I would not use the visualization of true color images, but rather go to the radiances values itself, and there you can do that in more detail. Okay, any other questions? If not, I guess we will call, thank you Hanna, to the next presentation, and the next presenter is Jorne Pohjankukka, who comes from the Finnish Institute of Natural Resources. I hope I get it right. And the presentation, which is hopefully coming up soon, is going to be from the peatlands, mapping peat thickness in Finland using airborne and satellite remote sensing with machine learning methods.
Thank you very much. My clock also. Great, yeah. So, my name is Jorne. Hello everyone, and good morning to the both the live and the online audience. I come from Luke, as was stated, and I'm a data scientist or a computer scientist by training. And I'm going to talk quickly about our work on mapping peat thickness in Finland. Yes. And there you can see the partners, and this work was part of the Catch the Carbon program. There. All right. Yeah. So just briefly about our institution, Luke. This is Luke. So Luke is a research institute under the Finland's Ministry of Agriculture and Forestry. It promotes business based on sustainable use of renewable resources, as well as the well-being and vitality of rural areas. The yearly budget is roughly 150 million, and there are about 1,300 employees. These are all old numbers, but roughly about this. So half of the institute funding roughly half comes from the state budget funding, and the other half from external sources. And about half of the staff there are researchers. The other half other experts, and a small percentage are research professors. Okay, so what was our work about? What is the background and the goal? So, as we all might know better, the conversion of natural peatlands to human uses, particularly through drainage, it contributes to the atmospheric and surface water emissions. And the effective mitigation of these emissions through policy steering, it requires detailed data on the peatland extent and its thickness. So, the goal was simple: to produce a new national level dataset on peatlands in Finland, utilizing machine learning methods and the latest extensive datasets. These datasets consist from multi-source remote sensing and GIS feature data, together with large soil reference data, about 3.5 million observations across Finland. So, so we modeled peat thickness classes. So we defined the peat thickness classes based on national and international peatland classification standards, including those of the World Reference Base for Soil Resources and the Intergovernmental Panel on Climate Change. We modeled the peat thickness in 4 classes, basically binary classification cases. Is there less than 10 centimeters, or more or equal or more than 10 centimeters, more than 30 centimeters, more than 40 centimeters, etc. So 4 classification cases in our modeling work. So the modeling pipeline, what did we actually do here? All our remote sensing and GIS data were basically pre-processed and unified together, consisting from, in total, 116 spatial remote sensing feature rasters, and with the 3.5 million soil observation. The peat thickness, as I stated before, the target rasters were binarized using these 10 centimeter, 30 centimeter, and 40 centimeter depth thresholds. After this preparing the data, we split this data into 70% for training our models, and 30% were used for performing the out-of-sample testing performance, which was roughly about 1 million test points. We built 4 random forest classified binary classification models, abbreviated as ERF10, ERF30, etc. And we selected the optimal explanatory features also for these models. After we optimized the models, the out-of-sample performance was then evaluated, and we produced various metrics, based the classification accuracy metrics, feature importance rankings, and we also investigated the correlation between the model's prediction accuracy and the model's uncertainty, which I will talk more in the following slides. And finally, after all the model optimization, we generalized the peat thickness over whole of Finland in a 50 meter times 50 meter grid cell size. So the nationwide generalization in 50 meter times 50 meter spatial resolution maps was implemented through parallelization and high performance computing using the CSC resources. So, simply put, the pipeline was this: we had the whole of Finland. The prediction or the generalization was parallelized. Each of those parallelized array jobs was multi-core processed, and the predictions were then merged in the final output. That is it. So about the outputs of our work. So first of our outputs was the probability of the peatland occurrence. So 4 different maps. So the first one, area 10, basically gives the probability for peatland extent and thickness of more than 10 centimeters, equal or more than 10 centimeters, equal or more than 30 centimeters, and etc. And the prediction out of sample accuracies, that is the test accuracies, were very good. So we got an AUC scores more or equal to 0.9. As the depth of the peatland thickness got, when the peat thickness got larger, or the more deeper the peat, the more difficult the task basically for the models was. But this was also quite natural, as we had even less and less observations the more deeper peat observations we were predicting. But overall, the results were, modeling results were really good. As the second output, we binarized these probability maps using probability thresholds, optimized probability thresholds. So these are just the derivatives of the maps you just saw there. Simply 0 or 1. Is there a peat of this depth or not in this area? And here are again different kinds of metrics, the AUCs there, what you just saw, and the overall accuracies and kappa values. So still quite good numbers there. And the threshold, a threshold value was used in deciding whether to classify a certain grid cell as having peat of this depth or not having. And this threshold value should be like 50% or 75%. This was optimized using the rock curves you see on the previous slide here in order to maximize the number of correct peat predictions and minimize the false peat predictions. Yeah. And as our third output, so we got the probability of peat occurrence of certain depth, classification, binarized classification decision, and also our third output was modeling the uncertainty of our predictions. So as we used random forest models for predicting the peat classes, these are committee models, so basically we had like a bunch, to be exact 100 decision trees, each of those being a model of its own, and we wanted to measure like how many, given a certain prediction, how many of these individual decision trees agree, or what was the maximal number of agreeing trees. So for example, if the whole random forest model said that there is peat, and like 90 of those decision trees agreed that indeed there is, and 10 of those decision trees said no. So that's like 50, what we call agreement value here. 50 is the worst case. It means that exactly half of those decision trees said no, there is no peat, and exactly other half said that there is. So that's like the maximum entropy case. It's like flipping a coin. Yeah, one model. Yeah. What we noticed was that there was a really high correlation between the models' agreement of the decision trees and the prediction accuracy. So here you can just see the peat probability and how it's what is the agreement basically. So those red on there's not much information on the plot on the right, but those red dots basically are where it's like flipping a coin. So it's quite sure about its predictions. Here, this is basically peat probability, more than 75%, and the green areas is where more than 75% of all the decision trees agree on its prediction. Here's more than 98%, and when you combine these two, you can get the occurrence of the peat with very high probability and very low uncertainty. Yeah. Okay, the last output was also feature selection. So which were the most important features? We noticed mostly dent-derived features were the most influential predictors, together with radiometric potassium and thorium. Depth to water was also noted. We did per feature correlation group importance, feature investigation to chat values. So basically you will see what are the most important feature groups and how they affect the prediction. Do they lower the probability or increase it? When we compared it to legacy maps, our new results improved both the thematic and spatial detail. So we got the accuracy improved, the spatial detail increased more than 25 times more, increase in detail. And the legacy and the new maps agree on the extent, but there were some changes from region to region. Our maps illustrated more new areas of peat. Yeah, so in conclusion, the new comprehensive and high accuracy peatland in 50-meter time 50-meter crystals resolution covers whole of Finland. Our work provides new opportunities for more localized management of peatlands. It allows for more accurate inventory of carbon stocks and emissions. Our output maps provide information of peat occurrence, thickness, and uncertainty of the prediction. Binary classification was chosen over regression because the available data that we have lack the resolution and sensitivity to grab very fine-grained variation in the peat thickness. And the dent-derived features were most influential predictors. Yeah. And that is it. Thank you.
Okay, we can have one quick question before we move on to the next presentation. Anyone?
We wanted to know what kind of thank you. I wanted to know what kind of GIS data we used here.
So this was given for myself. So basically, the partners that we have, they were the experts from GIS. So all those decisions came from our partners.
Okay.
So that is not as detailed like anything else here. But even in our published paper, you can also see more details.
Okay. Yeah. Thank you.
Yeah, thank you. Very interesting, excellent, clear presentation again. And next, bear with me, I'm struggling with this name. Yolanda Yalongo.
Close enough.
Welcome, and your presentation title is Assessing Air Pollution and Greenhouse Gas Emissions from the Mining Industry Using Satellite Observations. Take it away.
Thank you. Okay, thank you. So yes, I'm Yolanda Yalonga, work as a senior scientist at the Finnish Meteorological Institute, and I will talk today about this paper and then extra work that has been done at FMI concerning this assessing the emission from the mining sector. So the motivation for these works comes from...
Something wrong in the microphone.
Can you change switch?
Yeah.
Okay, yeah, it's making strange noises. Okay, this is better. Okay, so the motivation for this work comes from the increasing demand of energy transition materials such as copper, nickel, and other rare earth elements that are, it's rising because of these materials are needed for green transition. And at the same time, traditional mining sectors like coal are still ongoing in many countries like China, Mongolia, and Australia. And assessing the environmental impacts of these mining mineral extractions is quite important to be monitored to ensure that there is sustainable mining. And what we propose here is that to assess the atmospheric, so the emission into the atmosphere coming from both open pit and underground mining using satellite data. So I will show you two examples where we use satellite observation of nitrogen dioxide and methane to assess, that are both coming from mine sites. Nitrogen dioxide from the mobile fleet over open pit mines, and methane comes mostly from underground mine, but also at some location from surface mines. So concerning nitrogen dioxide, there are this nitrogen oxide emission coming from the open pit mines, and we focus here on copper mines. And these emissions are coming basically from the diesel engines from the mobile fleet, so every machinery that is used on the open pit. And the nitrogen dioxide is particularly useful. It's a polluting gas, but it's particularly easy to monitor from space. It's a short-lived gas, so it stays very close to the emission sources. It's quite easy to track fossil fuel emissions. And the satellite can observe this nitrogen dioxide quite easily through optical measurements. Now, what we expect is that the NOx emission will go together with, or we hope, we assume that that's the truth, go together with copper production or with other indicators of the mining activities, and that's what the hypothesis we try to test here. How much is the link between fossil fuel combustion processes and the mining activities? So we use data from the European Copernicus Tropomi instrument. This is a spectrometer measuring these optical measurements of sunlight that is coming through the atmosphere and back to the satellite. And it has been operational since 2018, so we have now 7 full years, but this study stops a bit earlier. And it measures both nitrogen dioxide and methane. I will show you an example later. The resolution of this type of instruments is the order of 3.5 times 5.5 or NO2 or worse kilometers. And this is like to give you an idea how these NO2 maps look like. This is an average over a few months of data at the beginning of the emission. And you can see in red, yellow colors highlighted the major emission area in the world, cities, industrial area, coal burning power plants, all where fossil fuel combustion processes occur. Now, that was just an average of concentration, what you saw here. That is what basically the satellite retrieval produces, but then we want also to assess the actual emission, so the sort of more, a little bit more quantitatively assess how the amount of pollutant released into the atmosphere in a certain period of time, which is sort of the relevant quantity that we ought to look at. And to do that, we use sort of data-driven method, such as this divergence method that basically works to highlight the sharp changes near the emission sources in these concentration maps. And it only requires information external from wind reanalysis, so it's quite a light method. So we focus on 14 among the largest copper mine in the world, located in South America, in Mexico, and in Arizona, and in US, and then in Zambia, the Copper Belt region. And we estimate these NOx emissions for each of these mines, these emission maps, as I described before, using this divergence method. And we obtain such type of map, and you can see that the enhancement of this red, yellow enhancement are on top of the mines. In some cases are very small, like in these Zambian mines. And then if we integrate over this around the area of the mine, we can obtain sort of annual emission of NOx. and if that are shown now in this y-axis, and then if we compare those to copper production, we found a somewhat approximate linear correlation, suggesting that the NOx emission increase with copper production. There is a link between fossil fuel usage and how much mass is moved over the pit of the mine and the emission itself. And so there are, of course, departures from this correspondence. Is not perfect, and that can be explained by several factors. Some of them cannot really clearly be explained, but it can depend on the efficiency of the mine or the technology used, how much is linked to fossil fuel combustion. The second example is sort of combines this analysis of nitrogen dioxide to also analysis of methane data. And here we focus on coal mining, where most of the methane emission come from in terms of like the mining sector. And as methane is greenhouse gas, so it accumulates in the atmosphere. It's not as friendly to study as emission as NO2 is, because it's accumulated and it's difficult to assess from where the emission of methane is coming from. They are coming from. But here we analyze one case to give you an example on different data that can be used to assess these emissions as well. So this is the Narisulkite coal mining block complex, which is located in southern Mongolia. This is basically mostly exporting coal from Mongolia to China. It's close to the border. And you see here the same NOx emission map that we saw before. And here we are able to, then again, with this blue line, calculate the NOx emission for each year. And build this time series, and we see that there is an increase starting 2002 and forward. Now, if we apply this, we could apply the same method to methane, or somewhat an adaptation of this emission estimation method to methane, but in this case the data is too noisy for that. So the only thing we could do is to calculate simple averages of methane concentration, also available from Tropomi. And what we can see, at least qualitatively, is that there is this similar increase in the last 3 years, also in the methane concentration, which might be sort of linked to the same processes that increases also NO2. And there's also a slight increase here in production of coal, and maybe we don't have data to verify that the production kept increasing. But that's something for the future to check. So to see indeed if this increase that we see in methane and NOx is actually reproduced by the increase in production, or if there's other processes that are driving that. But so there are other ways to analyze methane data. For example, this is one example. We could look at individual plumes instead of looking at data on average. And this is one plume over the same site in southern Mongolia, so this is the border to China. We can analyze individual plume and from those derive emission through similar statistical method. In this case it was about 14 tons per hour for these days. And then we can also use high resolution, much higher resolution data like those that are provided by this Carbon Mapper platform, where here the resolution is in the order of 60 meters. And here also we can estimate through similar integration method the emission that here accounts for 3.4 tons per hour. And so you see that there can be substantial difference between these two estimates, and they can also change day by day. So it's quite challenging to sort of build time series and assess how things are changing in time based on these individual plumes, and continuous monitoring is then required if you use this sort of method based on individual orbits. But this is, maybe combining these two is a good approach to get a better estimate of this methane emission. Yeah, this is my conclusions, and I hope I demonstrated that emissions from the mining industry can be assessed using satellite data, and that combining indeed coarse and high resolution satellite might improve, especially for the methane part, this assessment. And these are some acknowledgement. The projects.
Thank you, Yolanda. Any questions, comments? Yes.
Thank you for the interesting talk. I have a question with regard to this emission from Mongolia. Mongolia, the last time you were discussing. Do you see any seasonal variations in these emissions? I mean, because there is a Gobi Desert nearby. And time when, if I correctly read your slide, date corresponds to 5th of January. I think this is the time when there is some wind which spread all this aerosol all over the region, including Korea and Japan. So I'm wondering if you see this effect.
So yeah, actually don't know, because the plumes that are detected there, they are really few in a couple of years. There's probably 8 in total, so it's difficult to assess seasonal behavior of anything with this plume. This is part of the problem. It's not very, these plumes are not often necessarily representative of the whole year or that season. Can vary so much from day to day based on, but the effect of aerosol is actually also important because it affects the retrieval. So if there's a lot of aerosols, then the retrieval would be most probably affected by that, or like have a larger uncertainties. So, but it's difficult to say based on the data that are there. There are not many plumes detected. So, and that was also the reason why we could not apply this sort of averaging, like statistical emission estimation, because it's too little data to say anything about the annual behavior.
Okay, one more round of applause for Yolanda. We are well on time, and it's time for the next presentation from Sara Jokela from Huld. And Sara tells us about Sentinel-4 Level 1 reference processor. Go ahead.
Thank you. So, good morning everyone. My name is Sara Jokela, and I'm a project manager and software developer at Huld. I have a background in astrophysics, and I've been working at Huld for the past 6 years, mainly on the Sentinel-4 Level 1 reference processor. Now, I remember thinking on my first day on the job, what on earth is on-ground data processing? It doesn't sound particularly interesting. Well, I'm here today to tell you a bit more about it, why I find it interesting, and why it's important in the context of Sentinel-4 Level 1 reference processor. So before I talk about what on-ground data processing is, I first give a little bit of a context into the Sentinel-4 mission. So Sentinel-4 is part of the Copernicus Earth Observation Program. The program aims to provide high-frequency data on the Earth's atmosphere, surface, oceans, etc. to anyone for free. Sentinel-4 itself provides data on temperature, humidity, and trace gases throughout the atmosphere, specifically over Europe and Northern Africa. The Sentinel-4 instrument was part of the MTGS-1 satellite, which was launched in July of 2025. The satellite is very special because it's Europe's first geostationary sounder satellite. Now, the launch, of course, marked a major milestone for the Sentinel-4 mission and for our team, but the journey of the project began many years before, which I'll present a bit later. So the Sentinel-4 instrument itself contains 2 charged coupled devices, one which is in the UV-Vis wavelength range and the other in the near infrared. If you don't know what a CCD is, it's basically what old cameras or old phones used to use for cameras, a 2D grid of pixels which capture light. The Sentinel-4 instrument scans over Europe and Northern Africa every hour during the daytime and take 1 second exposures. These exposures are called raw or level 0 images, which are then downlinked to Earth. So now we get to the fun part, the on-ground data processing. So the level 0 data that I mentioned contains, among other things, the images that the Sentinel-4 instrument captures in the form of binary units. Now, binary units aren't the most practical units when further processing the data, so these need to be converted into a format that's more usable for the scientific and global community. And this is what level 1 data is. So in the Sentinel-4 mission, the level 1 data is in units of radians, so moles per second per meter squared per nanometer per steradian, a mouthful. But level 0 data and level 1 data are common terms in Earth observation missions, so these units can differ depending on the mission and the output. Now, Hult has developed the Sentinel-4 level 1 reference processor, which does exactly this. It converts the data from level 0 to level 1. Now, of course, converting units doesn't sound like it needs its own software, and indeed, only a minor part of the software does the unit conversion. The majority of the actual processing steps go into these correction algorithms. So, because the instrument contains impurities, imperfections, and physical constraints, we need to apply correction steps so that the final level 1 output that we receive is actually only the signal that the instrument captures coming from Earth. For example, the instrumentation and the electronics introduces an additional signal to the CCD called dark current, which has to be removed from the image. Another example is that each pixel on the CCD may behave slightly differently depending on the pixel response, and this also needs to be corrected. So I've calculated that the level 1 reference processor performs over 70 different correction algorithms, including the unit conversions when processing the data to level 1. And now, additional to this nominal processing, we also need to calibrate the terms that are used during the correction steps. The majority of this calibration is done, a minority of the calibration is done on ground during a calibration campaign when the satellite is still here. But the majority is done in orbit by our calibration processor. The actual processing is done on ground, but the satellite itself is in orbit. And in order to do the calibration, the instrument also has to take other images, such as dark measurements, light, white light source, LEDs, sun, and stars. Now, I know you're all probably very interested in seeing what level 1 data looks like, so I've gathered a few examples here. This is not yet Sentinel-4 data. This comes from the instrument data simulator. So I remember one of the first things I asked my technical lead when I started on the project was, how do we test our software when the instrument is currently being built and definitely not in space? We do this using the instrument data simulator, which was developed by S&T Norway for this project. Basically, that simulator simulates the data that one would expect to acquire once the instrument is in orbit. And it generates the level 0 data, and it's very critical for the early phases of the project. So what you're seeing on the left here is the measurement spectra for one 1-second exposure of Sentinel-4 in the UV-Vis detector. So on the horizontal axis, you see the wavelength distribution, and on the vertical axis, you see the spatial distribution, which is a very, very small slit of Europe. Now, I know this image probably doesn't give you much context into what you're seeing, But when you combine it with a full scan, you maybe start to get an idea of what Sentinel-4 actually looks like. So the image on the right is a combination of 3,400 images which have been processed into level 1 data. So imagine it like so. We take one wavelength slit from this image on the left, combine it with the 3,000 or so other images from the scan to form a map of Europe. And this is what our output looks like. So now the data is ready to be further processed by scientists into level 2 and further. So the title of this presentation is the Sentinel-4 Level 1 Reference Processor from Proposal to Commissioning. So I also wanted to give a bit of context into what goes into such a project. And here I present the timeline. So the project started in February of 2019 with the development, so already about 7 years ago. And already in March we received the first simulated level 0 data from the instrument data simulator. The first real instrument data was received from this enhanced engineering model, which was a preliminary model without any optics, so it only provided calibration data, such as the dark measurements. And after about a couple of years of intense development with a team of 3 to 10 people, we released the first version of L1RP in 2021. And about a year later, we started receiving the first data from the protoflight model, which is the model that's currently in space. And also the on-ground calibration campaign started then to calibrate some of these parameters that I spoke about earlier. Then a year ago, we released the second version of the L1RP, and not soon after, the launch occurred. We received the first data in September and October, and were able to process it. And currently we have commissioning activities into the satellite and the software, which are expected to continue at least into summer of 2026. Now, of course, the most special moment to date has been the first data, the first radiance data. This was such a special moment for our team. We gathered together with members from the ESA consortium over a Teams meeting and actually processed the data live with them using our software. And of course this was very nerve-wracking to see what does the output look like. Does it look like anything? And luckily it did. And here I am today to present to you the first images that ESA released in October last year. What you see here is nitrogen dioxide, ozone, and sulfur dioxide over Europe. In fact, there was some volcanic eruption happening in Mount Etna at the time, which you could now already detect with Sentinel-4. And yeah, these images are a clear indicator that the instrument itself is healthy and operational, and the software more or less works. Now, I could talk to you about Sentinel-4 for a long time, and please come find me if you want to hear more. But I wanted to give, as a conclusion, a bit about the things that we've learned as a team over the past decade or so. So the first thing is that the process is not linear from client to contractor. The client doesn't just tell us what to do and we blindly do it. Rather, we work as a team to create the best software with Airbus, with EUMETSAT, with ESA. And I found that very exciting and motivational, that I actually get to use my expertise from my studies in the project. The next thing is that testing with simulated data is only as reliable as the data itself. So some things you can really only verify once you're in orbit. For example, our assumption of what the star data looks like and the reality of what it actually looks like have been different. And this results in software updates that we have to do. And of course, for such a lengthy project, it's really important to remain flexible and not to have too strong assumptions, because everyone's understanding of the instrument, of the project, improves over time. So agile development is really an important part. But all in all, what I've taken from this project is that yes, we are creating a product in space, and that's really important. We're getting a satellite that provides us really important information. But indeed, the process of the project itself is more or less just as important. So working together with a multinational consortium is an extremely important thing in our current geopolitical environment. Each team brings something of their own to the table, and together we're able to improve our technical expertise as well as bring a peaceful future for Europe. And last but not least, I can't end the presentation without highlighting the fact that Poland won the ESA Excellence Award for Best Subcontractor last year for our work in the Sentinel-4 and Sentinel-5 projects. And I think a big part of that is because we brought not only a strong technical capability, but also a very international and cooperative mindset to the project. Yes, so I'd like to say thank you also to my project team for their hard work, and to Juho Miettonen, our project manager, as well as to ESA for wonderful cooperation.
Thank you, Sara, and congratulations to you and your team on the excellent work. Now, time for question or comments from the audience. You're all so excited. Okay.
Thank you, Sebastian from FMI. So you already mentioned it briefly, but I was very interested to hear what were the main differences between the simulated data and then the real data when you got the first samples?
So basically the Earth's halo. Yeah. So we did not expect that the halo coming from the Earth, so the star data is taken during the night time when the satellite is sort of behind and the sun is behind the Earth. But the Earth itself produces a big halo, and our algorithms couldn't expect that, so we need to do some sort of halo correction before we can start detecting the stars. So that's been the main thing that we found so far.
Any other quick question? Oh, okay, one more.
Okay, so my question is, first, thank you very much for your presentation. It was very, very good. Which correction corresponds the biggest, and which correction has made the biggest improvement with the data?
Probably the offset corrections. So there's quite a big offset coming from various electronics. So that one has a big impact. Also the stray light. So there's a phenomenon called stray light, which comes from like reflections between parts of the instrument itself, and they leave these weird patterns. So correcting the stray light has also been a difficult one, but effective, I think.
Thank you again, Sara. One more applause. Then the last presentation of this session from Tuuli Perttula. Tuuli tells us about tailored satellite-based air quality products for operational weather forecasting.
Hello everyone, my name is Tuuli Perttula, and I come from Finnish Meteorological Institute, where I work as a senior specialist both in air quality product satellite products, but also as an operational radar meteorologist. Waiting for my presentation to become full screen, but this work was done in the framework of HumanSat ACSAP project, and yeah, telling more about that either way.
Okay, thank you. Yeah, so this is my outline. I will first talk, introduce briefly the AC stuff, if you don't know what are units and stuffs, and then tell a little bit about our motivation, why do we need our new products, and then tell you about the questionnaire we made to FMI forecasters about what kind of products they would want to use, and then show you our new pilot products a bit, and then tell you about our future plans. Okay, so what is AC SAF? You have maybe heard about UMETSAT SAFs, but maybe you don't know what they are. They are UMETSAT satellite application facilities. They are basically centers of excellence for processing satellite data, and they provide operational data and software products to users. And UMETSAT has eight SAFs in total. The AC SAF is the UMETSAT satellite application facility on atmospheric composition monitoring, and it's led by FMI, and it has 11 other consortium members around Europe. And the products that are developed in the framework of ACSOF will then in the end be distributed to end users via the UMETSAT data portal. So what was the motivation behind our work? Like, why do we need even more new air quality products when there are already a vast amount of satellite-based air quality products? So in FMI, the weather forecasters are the ones that are normally contacted by the media in case there is some air quality issue, like a volcanic eruption or some Sahara dust coming to Finland, etc. And they often have to react quite quickly and answer to media questions without having special expertise on air quality. The satellite data that they normally use and they are familiar with are RGB images, which are not often really clear to interpret during air quality events, since they are more like air mass products or products for like weather phenomena. And also satellite data might be scattered across different websites, which is not very practical if you are in a hurry. So we see that there is a clear need for analysis-ready, easy-to-interpret satellite-based air quality tools, which would be visualized directly on forecasters' workstations. This is an example of how weather forecasters' workstation looks like. So you can basically show different kinds of data, which can be layered on top of each other. So for example, here we see an RGB satellite image and radar, and the forecasters can then select what kind of data they want to look like. And our plan is to visualize our data on, for example, on top of other satellite RGB images. Okay, so in the first phase of the ACSAF pilot, we made a questionnaire, and 13 FMI forecasters answered to it about their needs for the new products. And based on their answers, we created the following work plan. So the weather forecasters would like to have analysis-ready unitless products of wildfire smoke, which is our current priority in Finland, since that's like the main issue here, and also products of desert dust and volcanic ash. And we would do this by combining satellite data from multiple sources, and the appearance should be that whoever is looking at the picture would understand the situation at one glance. And the output will be visualized as layers directly on forecaster's workstation, and the code should be written so that different input data sources and end products could be added later on. Okay, these are the first data that we selected, And our criteria for our input data was that it should be available near real time, since we are making operational products, and we preferred HumanSat and Copernicus data here, but we are not limited to these. And for the products we use aerosol data from AAI and AOD products, and then other data which is used for identification of different aerosol sources, which would be CO, SO2 and dust products. And here is a little bit about how we, the rules, how we merge the data for final products. So first we clean and regrid the incoming data into cursor grid to be able to combine different data sources. Then we perform anomaly detection. Then we normalize the values between unitless 0 and 1, meaning low to high, to be able to merge different data sources, and then we combine the normalized values. For wildfire smoke, we use AAI and elevated CO values, and for desert dust, AAI and dust flak anomalies, and for volcanic ash, we are not prioritizing it at the moment, so it's still only SO2 data, but we will look into that later on. So this is the idea of how the products would look like. So it's really simple looking products. This is a volcanic eruption, and this is desert dust. This is a case where desert dust was transported to Northern Europe in March 24. But we are mainly concentrating on forest fires at the moment. So this is a product examples of Canada wildfires last June, when Canadian wildfire smoke was transported to Northern Europe and also to Helsinki, and the sky in Helsinki looked very red in June 4th, and this is also our product on the same day. And in the end, I think this is the best example to show what would be the benefit for the forecasters. So this is an example of our product during the Spanish wildfires during last August. So this is just MSG Severi without our product. So forecasters often look at these RGB images and try to find everything inside them. So you can maybe see clouds here, and then it's not often very clear where the forest fire smoke, for example, would be. So this is then our product showed on top of the MSG Severi, our wildfire product, which is based on AAI and CO values from different satellites. And the idea is that the forecaster could first look at our product and see it, okay, there is definitely some wildfires going on, and then maybe look at also some other products if they were interested in looking at the case more closely. Okay, so then I'm already in the conclusions. So in the first pilot project, we made new analysis-ready wildfire smoke, desert dust, and volcanic ash products for operational weather forecasters. And the weather forecasters were asked first what kind of products they would want to use. And these products have been tested offline to improve their quality. So we have selected several case studies during air quality events, and also tested this during for false alarms during times when there was not a certain air quality event present. and the algorithm has been adjusted after. And we are currently in progress to make a near real-time version of the processing system to test on FMI forecasters' workstations. And FMI forecasters have already promised to dedicate some of their working time to test and comment on the products. But at the moment they have been only commenting on the offline, like case study products. And currently we have been using data only from polar orbiting satellites, and the different overpass times of satellites make it harder to combine the data. But in the future we are preparing to use also geostationary satellite data, for example from NTG, to improve the time resolution and data coverage. So this has been only the first pilot, but we have plans to continue the work in the future. That was the last slide. Thank you.
Thank you, Tuuli. Very interesting, clear presentation once again, and a very nice example of how one can make really user-tailored products for specific user needs. Very nice. Any questions? Yes, there is one.
Have you considered using Actify hotspot detections as a part of input, or is it better to keep it separate, like it originated from here, kind of additional data for forecasters?
Yeah, we have considered of using all kinds of different data, and yeah, we would want to use as many input data as possible, but yeah, this was just the first pilot, and we had a limited amount of time and money to make it, but we hope that in the next phase of ACSF we get to explore new input data as well.
Yes, there's a second question.
Thank you for the presentation. I can see how this is used for the FMI forecasters. I would imagine this is also interesting for other people interested in air pollution. Do you have anywhere in your roadmap making this public?
Yes, like I said in the beginning, this is part of ACSF work, and in the end, if this will become an operational product, then you can get it from the HumanSat data portal, I guess. Here's also the ACSF leader.
Yes, and of course it depends who is asking the product. If you are interested to be as a user, just contact us and we will make it sure that you will get it.
Yes.
Later on, because that's our mandate.
Okay, I think this concludes our session. Thanks again for all presenters and audience for active discussion. And don't forget, there will be a second environmental monitoring session in the same room, 1:45. So after lunch, please come here and we will tell you more. Thank you.
Missä ne sukkulaat viipyy? Voidaan mennä hakemaan tuolta standeista.
Check. 7 aktiivinen operatiiviseksi tekemisvaihe, jossa silloin siitä tulee ihan operatiivinen tuote, se menee niin kuin kaikki kiinnostavat käytännössä käyttöön. Mutta jos teillä on jotain niistä oikein siihen teille, niin olen kiinnostuneita kuulemaan. Kyllä. Joo.
Yeah, perhaps if I speed up slowly compared to how the English
Ja siis se mielestäni tässä on kiinnostavaa se, että
that
on
would
niin
be
käyttäjä. Ainakin tälleen ensivilkaisuutta, koska
Ja se on nimenomaan se idea.
meidän ongelma on just se, että on kaikenlaisia sivuilla, siellä on jotain indeksejä ja ei ole tietoa sitten sitä, miten tässä kommunikoidaan ja niin suuri osa meidän analytikoista ei myöskään osaa tehdä dataa, että sitä pitäisi meidänkin jotenkin olla käsin aina omukaisissa käytännössä. Sitten kun tulee joku silleen, tänään tällaista, mitä tää on, niin mä oon silleen, että mä en mitä tapahtuu. Ootko keskittynyt kovaa?
No siis on tällä hetkellä jo
it actually stops.
Se on lähinnä vaan hyvä, kun tulee infrastruktuureihin, niistä on lähdetty vain jostain alueesta, mutta siinä jos sulla on sitä rajoitusta.
Niin kauan voidaan.
You don't need to stop it because
Niin, no mutta sen köyhyystilaa tehdään niin taas Suomessa taas niin toisaalta aika monen ilmiöt asiat.
Check.
this work? Okay, welcome. First speaker will be John. Sorry, I maybe pronounced it, but you can do it. But yes, the floor is yours.
Test. Hello. Yep. Can I put it here? Yeah. All right. Hey, hello everyone. My name is Imogen. I'm a doctoral researcher at the University of Vasa. My background is software engineering, and today, perhaps a better title will be the efforts of preliminary wake detection in the Takka offshore wind farm. And first it will be the project that this study is based on, then perhaps a couple of methodologies, then the results that we had so far, and as the project's still going on, what we will do. Also, just to mention that this is right now in a stage that it's still going on and not something finished, so it's not like publishable. So this is the Innovate, and you see the work package. There are many different people working in different work packages, and I will be, I'm all around the work package, I must say, but specifically I will be talking about work package 1, perhaps a bit of work package 2, and that's all. In the end, the main goal of the work package is that also coming up with what is the business opportunities or commercialization opportunities that could be done in the future. So you see on the left the offshore wind farm projects that is going on, that is planned, and on the right the overall wind park maps by the Finnish Wind Power Association. And our area here is there. It's not that yellowy area, there is even a small area there, and this perhaps the red area is the extension plan that will happen. And so this is our working area. There are 11 turbines, one of them is pilot, meaning that like it's just a smaller one compared to other. In total, the annual wind farm production is 157,000 megawatt hour, and the diameters is 130 meters, with the height of being 90 meters, and each turbine, except the pilot one, produces around 4.2 megawatts. Of course, the production rate or efficiency rate is a bit different, and the documentation for those also could be found in their own website. And why this area? First of all, it's the first offshore wind farm in Baltic region also that focuses on icy conditions. It's quite challenging to detect these type of analysis in this area. First of all, compared to what is available in the literature, the area is quite small, so less wind turbines. The usual literature is that like 40 wind turbines and such, and they are further into the sea, so they are not close to any kind of land that might affect the analysis or the signals. And you can also see like there's not the land on the right side is not enough. There's also some islands on the top end. But the one thing that we are lucky about is that the FMI has 2 weathering stations. One weather station is here, and one buoy here that gets the wave height or the temperature of the sea, which we also used. So the wind turbine, the wake occurs when the wind, right after the wind hits the wind turbine, it uses the kinetic energy on the wind. Then, of course, the wind starts to lose its power. Then, throughout the time on the downstream of the wind, then you get the recovery. This recovery, of course, might change depending on the conditions on the sea or the weather or the altimeter that these turbines are and such. And you kind of get this type of cone-shaped effect here that you see. And unfortunately, this will be the only image you see because, again, most of the images are not pleasing to eye. It's not so easy to understand also to see the wake. So this is like cherry-picked, one of the cherry-picked scenes that you see here. But if you analyze the same SAR image from this area with the same methodology, you will get the same results. So first, stability classification is done basically calculating the difference between the buoy temperature, sea temperature, and the land temperature. And if the sea is colder than the land, it's considered as a stable condition. If not, it's unstable. And then we also had another quality filter, you can call it, that depending on the phi angle that you can see here, between 0 to 30, this is 35 by the way, between 0 to 35, we only captured those scenes, and you can see the areas were right after the wind farm start working around 2017 September. And there was a total of 1.4 thousand scenes, and this is the wind throws, and we, for now, only use the eastern wind directions, and after the quality test, there was only 72 actually left. And when we were calculating our wake deficits, which I will show how also later on, we were actually able to get results in a way that it supports the way that wind and sea acts. So in the stable conditions where you have the colder sea, warmer air, and right in between you got the colder air, which is denser, so that a mixing of the temperature between air and water is more stable, so the deficit gets higher and it recovers slower, whereas in the unstable conditions, it was quite different, and the results were also statistically significant, and you can also see that the effect that I just described could be also seen there. There wasn't any extra improvisations on the wind measurement versus the SAR measurement case. So this is just the showcases of how it gets fit. The bias was that SAR was underestimating the wind around 0.70 meter per second. And comparing the literature that was happening that I mentioned, focusing on the bigger wind farms, these conditions were confirmed, and this was the first time, according to my Google search skills, the first time the SAR wake study on the Baltic Sea offshore wind farm has started to be conducted. One important thing to know that while these scenes were getting collected, the icy conditions were also excluded from this area. So I couldn't prepare a lovely image, but I prepared this. Perhaps you will enjoy a bit. For people that already knows about this, it's quite simple, but what happens is that first we remove the thermal noise, and what happens is I need to stop the video right here, and when I stop it goes, unfortunately. What happens is that this thermal noise occurs not due to the reflectance or the ocean, but it's the instrument itself causing this noise, which is quite predictable, and not in this image. The images itself is real, but I artificially created that U-shaped noise to see how it looks like, and since it's predictable, it could be also easily removed. And to be able to remove this, there's a lookup table that also is provided by the product itself. So you basically do the calculation, and you will see that these tend to, edges of the SWATs, when they are getting collected to each other, tends to be whiter. And then once they get removed, the noise becomes more uniform, and then ready for the calibration. And when it comes to calibration, we do also use another lookup table, and from digital numbers, which is the arbitrary numbers, perhaps it doesn't physically that meaningful, but it is the magnitude of the backscatter. In that sense, needs to be converted to the sigma naught, and I will use the sigma from now on also the presentation to be able to get meaningful information from our image. And how it looks usually is that these are of course artificial. Oh, my bad. Oh, now we need to This is hard to use, sorry for this. So what happens is that once you get the backscattering information from there, already there you can actually start to see the wake effect, and which is shown in this matrix. You will see there will be a smaller number here in the middle, which is our synthetic wake information. Then of course the amount of pixel is per scene is much higher. It doesn't need to be only 10,000 to 10,000, it could be bigger, smaller, depending also on your subset area. And when, after the calibration, the areas becomes much more visible to understand in decibels. And then after the calibration, now you are ready for the wind retrieval itself. Of course, right before the wind retrieval, there is another filtering going on about how much of the area was actually able to captured by the SWOT, what was the quality of that, again the quality filtering that we done. But these are proportional to each other, the wind speed, the surface roughness, and the sigma naught. Then comes the wind retrieval, which we use the C-Mod 7. C-band geophysical model version 7. They have 3 inputs: the backscatter we got, the incidence angle from the satellite geometry, and the phi that we also calculated. And how C-Mod 7 tends to, and this is another visualization of how phi angle reacts depending on the satellite path, and when we got the phi closer to the wind direction, we get the capillary waves backscattering a much higher ratio on the sigma naught, so it becomes much easier to detect. Also, this part in particular is anisotropic, so it means that depending on the angle you look, it changes, the values change. So and the cos theta and cos 2 phi and the cos 2 phi needs a wind direction, because if you just try to get it, then you will have multiple locations within the observed sigma naught that we have. And once we get the wind direction, in this case from FMI, that we can now have our lookup table depending on the incidence angle, the phi angle that we calculated, and now we know the backscattering. Then from the lookup table, we know, okay, what is our wind speed within this given calculation. So you inverse the algorithm in a way. If you know the wind speed, it's much easier to get the backscattering in this sense. And by this, we were also able to get the wind speed itself. And so far what has been done was the wake detection confirmed in a way that given this really precise conditions confirmed, you can actually get the wake deficit calculated. And we confirm also the prior to literature that we are getting the same results, expected results also regarding on the physics. And luckily, after 1 year, we had the NDA agreement going on. So we will also get the SCADA data, so we can further continue our calibration and decision making on the power loss, and perhaps then further research will be automating these calculations and giving reports. One other thing is that I don't know if this offshore wind turbine has this technology going on, but some offshore wind turbines on purposely misaligns their yaw alignment, so they on purposely do not look directly to the wind so that the wake deficit gets less on the wind turbines on the back, and they get less stress on the other wind turbines due to this. Yeah, that will be all. And there are quite a lot of ways to continue. For example, we are not sure when we are looking at if all the wind turbines are working. So we assume that all the wind turbines are working and all of them are adding this effect on the wake deficits. We don't know, we didn't check different baltimetry since this Baltic area has different baltimetry compared to other research areas. We don't know how this is affected. The bottom of the wind turbine itself is designed for these conditions, and there is no other wind turbine like that so far. And how that also affects the wakes itself is another question. Yeah, thank you. Any questions?
Time for a few questions.
Oh, okay.
I may also have one if there will be.
Oh, perfect.
But let's first ask the audience.
Yeah. Ah, yes, please.
Yes, so from what I see, you are measuring the wind speed by the roughness of the sea surface area.
Yeah.
And so this method will not work with any kind of turbine that is processing inland.
No, it won't. Yes, so this is for the wind deficit on offshore wind turbines.
So like, what are the percentage of wind turbine that you can measure versus what are the amount of wind turbine that you cannot use this method?
Oh, so if I understood correctly, are you asking what are the other areas that I cannot use this methodology?
I mean, what I mean is, is it working? Maybe I just. So, what I'm trying to say is, like for this method, how many percentage of the wind turbine are you like? Can you use it on?
How many percentage of the wind turbines I can use?
Like just
anything that is on the sea that could be used, and assuming right now that it's not covered by the ice, totally covered by the ice.
I see. Okay.
Yes.
So like 20%, 30%, or?
Unfortunately, I don't know compared to
Right.
how many wind turbines on the land to the offshore wind things. But on the Baltic area, these are the only ones. And the expansion, by the way, I forgot to mention, will be having 40 wind turbines, and it's already confirmed that they will start with 2 pilot wind turbines, much further on the sea. So if there's anyone also from FMI that can work with where to put buoys, there's a great opportunity to expand the buoys. There's actually another buoy further in the Baltic Sea, but more the merrier, I would like to say.
All right. Thank you very much.
Yeah, thank you. And I guess you also had a...
Okay, I think the next speaker
All right.
will be Dennis. I will not ask it. We are behind the schedule, I think. Yeah, the next speaker will be Dennis Demchev, I think. At least I saw his name there, but there is. Is the next speaker here or? So if we don't have the next speaker, I guess should I give my presentation first and see if he will appear? I point this. Okay, it's not lost. Okay, good morning. I'm Juha Karvonen from Finnish Meteorological Institute, and my topic is related to sea ice concentration estimation from 12 polarized C-band SAR and microwave radiometer in collaboration with Marko Mäkynen. Where is the... Stopped working. Can you change it manually then? Typical technical problems. Okay, first the outline. First, of course, the study area, which is the Baltic Sea. Then some words about the SAR data and also microwave radiometer data and pre-processing of the data, about the methods, estimation results, and some conclusions. Next slide. Does it work now? Okay. For a while. Okay, the study area is also the Baltic Sea, shown here. I guess it's familiar for most of us, but most of the sea ice occurs in the Gulf of Bothnia area and Gulf of Finland, eastern parts of Gulf of Bothnia. Nowadays, earlier days, there were more sea ice, but at least the last few winters have been quite mild, and the sea ice has mostly been in the Gulf of Bothnia and eastern parts of Gulf of Finland. Okay, the data we were using is Sentinel-1, mainly Sentinel-1 ground range detected minimum resolution extra wide swath data, which HV polarization with a swath width of 400 kilometers and spatial resolution of 20 by 40 meters. It's about the same as for the other instruments we have also used in this study, which are RADARSAT-2 and radar constellation mission data. They also are using this HV polarization combination, and they have a little bit wider swath, about 500 kilometers. But the Sentinel-1 dataset consisted of over 600 images. Here are the monthly distribution from December to May, also in parentheses, and this is for the winter 2018-2019, and we used about 200 images for training the neural network for Sentinel-1, and also this RADARS-2 and radar constellation mission data consist of similar amounts of training data, but they cover 3 winters. Okay, here is shortly the Sentinel-1 processing chain. It's quite similar for the other instruments. We perform calibration and quantization for both the channels HHV and also compute the incidence angle grid, and then we perform an incidence angle correction only for the HH polarization channel because the incidence angle dependency is higher there. We also perform some noise filtering for the cross-polarized HV channel because there is more of this thermal noise. Then we perform blunt masking, and then we have analysis ready, HH and HV SAR data. Okay, then about this microwave radiometer data, which is this AMSR2 instrument, and there we totally use 36 features, which are based on the brightness temperatures, but these features are the polarization radius and gradient ratios, which are computed like this, so they are kind of differences between the different polarizations divided by their sum, and then there are also these gradient ratios are differences between different frequencies and with the same polarization. And because there are so many features, we performed a dimension reduction based on this partial least squares algorithm, which is can be considered as kind of a combination of principal component analysis and linear regression. So it's specific for a certain feature. We are, in this case, the CI's concentration. So it's kind of optimal for this parameter, CI's concentration. And we only used three first or three most significant PLS components. Okay, the method was actually the neural network model was the UNet, which has, in this case, 6 layers, 6 decoder layers and 6 encoder and 6 decoder layers. And in the bottleneck part, we also have included a self-attention layer to take care of the larger context in the image. And UNet also has these skip connections between the encoder and decoder layers to better represent or maintain the resolution of the original image data. Also, the loss function has been modified such that we have a linear combination of 3 components: categorical cross entropy, absolute difference, and also the distribution entropy. Okay, here is an example of the inputs. On the left, we have the SAR image data, which now has 3 input channels. It has a HH and HV channel, and also included the HH-HV cross correlation as a third channel in the SAR input. And the AMSR2 also consists of this polarization and gradient ratios with the reduced dimension, reduced to 3 dimensions. So it can be represented as a false color image like here. The SAR imagery is now also represented, and then the results are in 500-meter resolution. Also, the microwave radiometer data has been resampled to the same resolution. Because there are some computational limitations in the training phase, so we trained the algorithm using 256 by 256 pixel windows. Also split the input image and then recollected it to the whole image. The windows for the training were randomly sampled from the training data set, and about 200,000 windows were used in the training of all the 3 instruments. Okay, the Adam optimizer was used, and the initial learning rate was set to this 10 to the power minus 5. And we ran 60 training epochs. It could also have been less, but this is enough. But anyway, the weights were selected such that it was the weights were the weights with the lowest validation loss in after the epoch with the lowest validation loss, and they were selected for the inference part. Okay, just to show the loss evolution during the epochs, we can see there is this training loss and validation loss. They to very low values, also the validation loss. So the accuracy was something like 0.98 or 98% or 99% even after the training for the validation data. For the training data, it was even better. So at least training shows quite nice results. But yeah, okay, I already mentioned this that 60 training epochs were done and how the weights were selected then. Okay, and the invariance part, the resulting windows merged to a larger image. Okay, as said, the window size restricts the field of view, and for the self-attention mechanism, which tries to take the whole window size into account. But now the 256 by 256 window means that it's 128 kilometers. Okay, the model is actually such that it classifies the sea ice thickness into 12 classes, 11 sea ice concentration classes. Sorry, I said sea ice thickness, I meant sea ice concentration, intense, starting from open water and ending to bare ice 100%. And then the 12th class is the background, which means that there is no data or land. Okay, now when we perform the classification, the model provides a probability density function of the classes, and sea ice concentration is based on the probabilities. It's assuming that we have a Gaussian distribution around the highest probability, and we can, from that we can get a more precise estimate for the sea ice concentration, trying to find the actual peak of the Gaussian distribution. Another approach would be, of course, to use the expectation of the probability density function. But now it's trying to estimate the peak value of the Gaussian distribution. And as we get the probability density function, we can also estimate the uncertainty, for example, in the form of standard deviation from the probability density function. Okay, then we performed comparisons between reference data sets. We used the ice chart, sea ice concentration, which was also used in the training of the neural network, and then we also derived the sea ice concentration based on this optical and infrared data from MODIS. It was estimated for each ice chart polygon based on this open water sea ice classification from the MODIS data, and the same thing was done for Sentinel-2 data. And also we compared it to the operational University of Bremen ASI, artist sea ice algorithm, using AMSR2 microwave radiometer. And yeah, okay, just to mention that MODIS has a lower resolution than Sentinel-2. But yeah, but when we derive these reference data from MODIS and Sentinel-2, here is just an example where we can see sea ice in the rightmost, or in the, northeastern parts of this image. But the first one is on the left is the ice chart, the ice concentration. The middle one is the MODIS ice concentration, and on the right there is this Sentinel-2 sea ice concentration. And we can see that they differ, especially this Sentinel-2 sea ice concentration is lower in many parts for example, the modesty ice concentration, and this is one problem that even the reference data, they are not very consistent. But anyway, we performed this comparison. Here are some results showing. The first one is comparing the ice chart and the Sentinel-2. The second row is ice chart compared to the ASI algorithm. And then there is this our algorithm compared to the ice chart, which shows quite nice nice results, of course, because we have used the ice chart for training the neural network. Then it should be able to make good results or provide good results that resemble the ice chart. Compared to the ASI, the results are worse, but of course ASI has its own inaccuracies and it has a lower resolution than our algorithm. So this may be one reason for that. But then when compared to the Sentinel-2, there is also quite large differences. For example, the root mean square difference is almost the same as for this ASI. And when compared to this modest data, the result looks better. And also we also compared this ice chart data with all of these other reference data. But anyway, in general, the results look quite okay. Here is just a comparison of the categories. We can see this, whatever this violet, maybe this color when compared to ice chart, and we can see that in most cases the classes correspond to each other quite nicely. There are some exceptions, but they probably go to the adjacent classes. But anyway, this is kind of an expectable result because ice charts were used for training the algorithm. Some examples. Here is an example of 15th of March 2019. On the left we have the ice chart, the ice concentration. In the middle, the algorithm result, and on the right we have the uncertainty provided by the algorithm. So we can see the areas where the estimation is more uncertain. We can see that it's in many areas of the sea ice, but in the open water areas it's not that uncertain. Another example, which is using all the three instruments as its input from last week, it's using Sentinel-1C radar constellation mission and radar-2. The blue area in the middle one, which represents the estimation results, there in the southern parts means that there is no SAR data over that area. But in the ice-covered, most of the ice-covered areas, there exists data. And we can see, if we compare to the ice chart on the left, we can see that it's quite similar, but there are some differences, of course. But this may be due to the fact that the ice chart data is not that exact anyway, because it's based on providing the ice concentration for large polygons, and this automated algorithm provides the estimates in much higher resolution. And there is also the uncertainty. Unfortunately, the scale is not very good in this case for this uncertainty, but in this case the white areas or whiter areas there indicate larger uncertainty. Okay, then a few words about possible future directions and some conclusions. Okay, the operational test is now ongoing, and we started in the beginning of this season. And after the season, we'll perform a thorough evaluation of this. So it will, at least we hope that it will be fully operational as part of the Copernicus Marine Service sea ice tag next winter. And yeah, it's now applied to all these available C-band SAR data, and they have been trained it separately for all these 3 instruments. And the sea ice concentration is also published as part of the Copernicus Marine Service as a daily sea ice concentration mosaic. Okay, and we are continuing the algorithm development and analysis and optimization as part of the Research Council of Finland project. We have just started last autumn in collaboration with the Tampere University. And the first results of this new project will be published in this international conference, image processing, in September this year in Tampere. And we are planning to go to a higher resolution, not much higher than 200 or 250 meters, and also going to use a bit larger windows to cover about similar area in each window, so about 100 or 128 kilometers that it was. It will be 128 in the 250 meter resolution. And yeah, the algorithm seems to work quite nicely also for Sentinel-1C, even though we were able to use Sentinel-1B data for the training, because the Sentinel-1C data, we only have Sentinel-1C data for this season, and now we are collecting, of course, the data. And if seen necessary, we will train the algorithm with the Sentinel-1C data after this season. I guess this was the last slide. Okay. Then I'll change to be chair again, and please, any questions?
Yeah, any questions? Doesn't seem like it. We're a bit behind schedule because one of the presenters wasn't here. Maybe he's here now. Dennis Demchev. Sorry for the bad pronunciation. Yeah, I don't think he's here. So I think that's all the presentations we have. Thank you.
Good afternoon. I hope you have enjoyed your lunch. And welcome to the afternoon session of environmental monitoring. We had the first session in the morning, and this is continuing from that. My name is Pekka Hurskainen. I come from Finnish Environment Institute. Next to me is my colleague Jenni Attila from the same institute. So we will be chairing this session. And the first one is Hibiki Noda from National Institute of Environmental Studies in Japan, and she will talk about assessing 21-year changes in the phenology of cool-tempered deciduous forest in Japan using in-situ remote sensing. Welcome.
Thank you. Good afternoon, everybody. I'm Hibiki Noda from Japan. Today, I'd like to introduce about our research activity targeting vegetation phenology by using in-situ remote sensing technique. Well, in Japan, deciduous forest is one of the very common vegetation, and in a deciduous forest, there are large seasonal dynamics in environment, especially one of the biggest one is because of canopy phenology. During winter, there are no leaves in canopy, but from spring to autumn, there are large amount of leaves in a canopy. And also, large part of Japan, we have heavy snow. So snow cover period also one of the big seasonality of deciduous forest. And these seasonal dynamics strongly affect on carbon cycles. And recent climate change strongly influence on these seasonal dynamics. So to understand the effect of climate change on carbon cycle of the forest, we have to monitor the seasonality of forest. To monitor the canopy phenology, satellite remote sensing has been widely used. However, sometimes the time resolution or spatial resolution is not fit. On the other hand, if we use ground-based remote sensing technique, I mean in-situ remote sensing technique, we can get the data with high temporal resolution and fine spatial scales. And also, it is easy to integrate with ecological data like eddy covariance data. So we have developing in-situ remote sensing site network, so-called PEN, Phenological Eyes Network. It started from 2003. And aim of the network is to validate terrestrial ecological remote sensing with a particular focus on seasonal change, including phenology in vegetation. Now, 45 sites are joining us, and also some sites are overlapping with FluxNet, Flux eddy covariance site, and also long-term ecological research networks. If you are interested in our activity, please check our website. One of the PEN site, Takayama Deciduous Forest site, so-called TKY site, is one of the longest observation site in PEN. We started from 2003. TKY is located in central part of Japan. This area is mountainous area. The elevation of TKY is 1,420 meters. Here is a cool temperate region. This forest is dominated by Bettera almani, Japanese birch, and also Quercus crispra, Japanese oak. And one of the unique features of this forest is snow cover. This area is a deep snow area, and sometimes snow depth reaches 2 meters. And another unique characteristic of this forest is understory vegetation. Understory of this forest is dominated by evergreen dwarf bamboo grass, so-called Sasa sinanensis, covered understory of this forest. In this forest, we have measured with spectral radiometer just above the canopy. This is the canopy access tower. Here we have the spectrometer, and also we have automatic digital camera for the canopy photos and also understory photos like this. And in this study, we used 21 years from 2004 to 2024. And for this study, we calculated two vegetation indices. One is green-red vegetation index, GRVI. It uses reflectance in green and red. And also, we have calculated the NDVI. And here is a seasonal pattern of GRVI and also NDVI. For different symbols shows the different years. As you can see, those show the similar pattern, but there are some yearly variation. So to identify the yearly trend, we determine the timings from these seasonal pattern. For GRVI, today we just focus on spring phenology because of limitation of time. So for GRVI, we determined three timings. One is the day when GRVI reached minimum, and the other one, second one, is the first day when GRVI exceeded 0, and the day when GRVI peaked. For NDVI, NDVI pattern shows two curves. So NDVI was fitted to combine the logistic models, and we determined the inflection point of each curves, and also we determined the maximum, the date when NDVI reaches the maximum of each curves. And also we checked with the canopy cameras. For NDVI, for GRVI, the first timing, the minimum of GRVI indicates just after snow melt, and second time of GRVI, this is the onset of leaf expansion, and also the peak timing is the completion of leaf expansion. For NDVI, the first curve, the inflection point of first curve was middle of snow melt, and the maximum part of the first curve was just after snow melt. And also we checked the understory camera. In this timing, we can see the leaves of sasa at understories. Well, it means the first curve of the NDVI is caused by sasa leaves. As the snow melts, sasa become exposed, and because of that, we can see the first curve like this. And also, we checked the second curves. Second curve was caused by the leaf expansion of canopy trees. And here is a yearly trend for 20 years for timings determined by GRVI and determined by NDVI. These are timings of snow melt timings. And both indicates that snow melt and exposure of sasa has occurred earlier, about one day per year. So it means 21 days during these 21 years. And also we checked the leaf expansion timings. It was about onset of canopy leaf expansion was also occurred earlier, but the speed was 0.5 days per year. So the speed are different between snow melt and leaf expansion. It means from snow melt to onset of canopy leaf expansion, there are kind of spring window for understory species, so-called pre-leaf period. there are no canopy leaves and no snow. This period is very important for understory species, especially here we can see the sasa canopy here. And during this period, understory species photosynthesis. So to understand the effect of this change on the carbon cycling, we analyze the eddy covariance GPP. Here I'm showing the daily GPP for 21 years, and we assume that before onset of canopy leaf expansion must be mainly due to photosynthesis by understory sasa. So we analyze the cumulative GPP before onset of canopy leaf expansion, and here is the result. Here is the GPP before canopy leaf expansion. The GPP during this period getting larger. So it means because of climate change, the carbon uptake by understory vegetation getting larger in these 21 years. As a summary, over 21 years, both snowmelt timing and canopy leaf out advanced in cool temperature deciduous forest at the Takayama site. The advance of snowmelt was larger than that of canopy leaf expansion, creating a longer period of high light availability in the forest understory during early spring. This extended bright period led to an increase in cumulative GPP before canopy leaf expansion, indicating strength contribution of understory vegetation to forest carbon uptake. That's all. Thank you very much.
Thank you so much, Hibiki. Excellent, very interesting, clear presentation. I'm sure there will be a lot of questions, so who's going to be the first one? There's one. Yep.
Thank you very much for a nice presentation. I was curious, the GPP that you showed us, is it from a particular period before the tree's bud burst, or is it a singular time step?
Well, we assume the timing of onset of canopy leaf expansion. I mean, the date we determined with GRVI. We assume the timing of this timing. Before this timing, GPP is mainly due to photosynthesis by understory vegetation. So, well, yes. Well, we determined with the timing of this, and it depends on years.
Yes, there's another one.
Thank you for the nice presentation. I was thinking, have you studied the effects that this phenomena has on the ecological succession in the forest?
Thank you for a very nice question. Well, yeah, we are thinking about the effect of ecological succession. So as a next step, we have to make some analysis about it.
Maybe one more question. Jenny, you had something in mind?
Yes, thank you for your very nice presentation and interesting results. So I was actually my question is about this slide, so it's really nice that you have it on. So you had this just after snow melt with GRVI and then NDVI just after snow melt. So have you plotted these together so that they are exactly the same time when you have this peak? The minimum.
Thank you for nice question. Well, yes, we also we compared these data and some, well, basically the timing of snow melt almost same, but sometimes because we just for GRVI we just pick up pick up 1 point. On the other hand, in NDVI we fit the model, so well, the timing of GRVI looks a little bit unstable. It depends on the fluctuation of each day. Thank you.
Thank you again. One more round of applause. Yes, I forgot to mention there's one change in the program, so Krista's presentation will have, unfortunately, is cancelled. She's not able to present, so we have one less presentation. But now the next one is Amanda Ojasalo from University of Helsinki, and you will talk about monitoring vegetation phenology in Helsinki with satellite observations. So now we are going to more local scale monitoring of phenology.
Hello everyone, my name is Amanda Ojasalo and I'm talking about monitoring vegetation phenology in Helsinki with satellite observations. This is an ongoing work, part of my PhD project, and I'm working in the University of Helsinki and Finnish Meteorological Institute. Let's start with a brief background about urban vegetation phenology and what makes it special. In urban environments we have these many different processes such as the increased temperature, CO2 levels, human management practices, heterogeneous soil properties, and diverse species composition which shape the seasonality of urban vegetation and makes it a bit different than the seasonality in non-urban areas. So there are these shifts in start of season and end of season when comparing cities and their outside areas. For example, the start of season often starts earlier in the city than outside of it. But cities are very heterogeneous environments, so there's diverse growing conditions. We have very highly urbanized areas, street trees, and then cooler urban forests and parks. And then these areas are of course very different, and what we are interested in this work is what is going on in the city scale. When we observe phenology with satellites, commonly vegetation indices such as EVI and NDVI are used, which capture the seasonality of the vegetation greenness. There's also other indices, for example, the plant phenology index, which is designed to capture more the GPP seasonality, and also SIF, which is solar-induced fluorescence, which is the signal emitted by plants when they photosynthesize. So SIF is a bit different compared to these optical vegetation indices. There's also difficulties in observing urban phenology because of the heterogeneous land cover. There's a lot of mixed pixels, pixels containing various different surface types, which then creates uncertainty in phenology estimates, especially at large spatial scale. So in this work, we are interested in how phenology varies spatially and temporally in Helsinki across different vegetation types, how the phenology of these different vegetation types respond to climate variability, and how small-scale phenology patterns compare to larger-scale observations. On the right side is the data we are using. The main data is from Sentinel-2, Plant Phenology Index Time Series. In this work, we are interested in two metrics, start of season, so SOS, and end of season, EOS, from which we have defined from the PPI time series as dates when the fitted curve reaches 30% of the average amplitude of all years. So basically this means that in each pixel, the same PPI value in every year is the start of season and end of season value, but the dates when these values occur are shifting. This is what the data looks like for the whole Helsinki. So we have years 2018 to 2023, and the spatial scale is 10 meters. Above is the start of season for 2021, and as you see, it is a bit more smoother than the end of season, which has a bit more of this very small scale spatial variation as well. Then what we did next is classify the vegetation in Helsinki into different classes, which are conifer trees, broadleaf trees, mixed trees, urban trees, grasses and meadows. Urban trees are the trees in these smaller units, such as street trees and trees in building yards, and then these other tree classes occur in more vegetated areas, in urban forests and some urban parks. So as you can see, conifers have the earliest start of season. In most years, also grasses have their start of season quite early, but meadows are consistently the latest class to start their growing season. Meadows are also the earliest, having the earliest end of season, but then there's more variation in other vegetation classes, such as urban trees and grasses. Then we wanted to find out what is causing this variability, so we did this random forest model for each vegetation class and for the start of season and end of season. Here I am showing end of season results for 4 different vegetation classes. On the left side, these are the 3 top most important model variables for these classes. And on the left side, you can see how summer radiation and summer temperature are the most important variables for conifers and broadleaf trees, with higher radiation and temperature contributing to later end of season values. But for urban trees and grasses, we see that these precipitation variables become more important. These are also the classes that are more exposed to urban effects, like the elevated heat and drought. So that is probably what we see here, that these classes are therefore more sensitive for water availability. Then let's move on to comparing phenology at different scales. Here you can see 3 different data grids. Red one represents tropomy pixels at best resolution. This is not the actual data grid because it has an irregular pixel size, but at best the pixel size is 5.5 to 3.5 kilometers. Then at blue we have a 250 meter grid, and at 10 meter grid at gray, representing the Sentinel-2. So this is to illustrate you what kind of scale differences we are talking about and what that means in the urban scale, how much different kind of structures there can be present in one pixel. This is what the comparison for start of season and end of season looks like for the Sentinel-2, Tropomisiv, and MODIS vegetation indices. So for start of season, it's the products are more closer to each other than in end of season, where SIF and PPI aligns best despite the huge difference in spatial resolution. And EVI and NDVI are showing consistently later end-of-season values. This can be due to the difference in greenness phenology and photosynthesis phenology. And also, although SIF has the lowest spatial resolution, as the signal comes straight from the plants, it is maybe not as affected by the mixed pixel biases as MODIS. Then, little bit what we are doing next. We have these 10 trail cameras around Helsinki capturing daily images, and we will then compare these greenness time series from these images to different vegetation indices from Sentinel-2 to see how they align. We are also building this Urban Phenology Observatory webpage where you can explore the data and compare different indices from these sites and also compare them to different environmental variables. So as a summary, there's clear differences in phenology across vegetation types in Helsinki and year-to-year variability, especially in the end of season. Vegetation types respond differently to climate variation, for example, the urban trees and short vegetation showing sensitivity for water availability. And the PPI and SIF phenology aligned best, which then highlights the potential of SIF for capturing broad-scale urban phenology, and also the ability of PPI to detect photosynthesis seasonality, similarly to SIF. Thank you.
Thank you, Amanda. Great. Now, questions? Yes, Sakari.
Thanks for the clear presentation. I think it was your second or third slide, if you can turn a little back on the presentation, where you had the continuous time series, this one, yeah. I noticed that you probably have some kind of smoothing here because the line doesn't reach the highest values in each year. And since your start and end of season are tied to the maximum value, do you think this affects also the results because you are sort of tying your start and end to the maximum value, which in your uniform line doesn't reach the actual highest ones? Thank you. I know it's a hard question, but...
Yeah, thank you for a good question. This is done with software called TimeSet, which is quite widely used in phenology research. We tested all different fits that are possible in TimeSet. This is a double logistic fit, and it aligned best with the observations. Yes, it's not capturing all the highest values, but yeah, that can cause some effect. But in this work, I think the relative differences are more important than the absolute value of the start of season and end of season. Yeah, so we did also test different defining methods for the start of season and end of season, but the spatial patterns remained. So, yeah, thanks.
I have one question related to this same topic. So I assume that you processed this yourself from Sentinel to this start of season and end of season, right?
Yes, I actually forgot to mention that the PPI time series is from Copernicus, but yes, I did do the fitting and the start of season, end of season defining. Yeah.
Exactly, good. Because, yeah, I have tried myself from the Copernicus land monitoring service. There is this ready products, phenology and productivity parameters. And there is also start of season, end of season. But they are suffering from cloud artifacts. So did you look at that data yourself or at all, or you decided to? What was the reason you processed it yourself?
Thanks for the question. Yes, I have used that product myself as well in some earlier work. The reason for doing this myself is that because that's for the whole Europe, it's maybe not as suitable for example, high latitudes. If I remember right, that data has this winter gap filling of 5 percentile of the values, which in our area seemed too high because we have those clear sky gaps, especially in the low values. So we used lower percentile and a bit more tweaked suitability to Helsinki. But yes, I have used it, and it's, yeah.
Good. Now, more questions?
Very nice talk. Suggestion for the phenological monitoring in the field. Did you think about using like citizen science approach? So expanding your trail cameras so people can contribute their own imagery?
Thank you for the nice question. Actually, I haven't thought about that very much, but it's a nice idea and I will think about it.
Maybe time for one more question, if any. Not, then thank you again. Let's give more applause.
Okay, and then we will move on to a different topic. Let's wait for the slide first to come up. So the next presentation is from Sakari Väkevä from the Finnish Environment Institute with a presentation titled CMEMS NCP for Finland on coastal nutrients, total phosphorus and chlorophyll A.
Thank you, Jenny, for the introduction. In this presentation, I will be focusing on a smallish project which relates to coastal nutrients and what their reflection is in the coastal water bodies of Finland. I know that some of you are probably bewildered by the acronyms in the title, but I will come back to that soon. By coastal nutrients, I mean in this case total phosphorus especially, and then chlorophyll is the variable that reflects sort of the impacts of nutrient availability in the coastal water bodies. I didn't put here a map of the Finnish coast, but as many of you know, it's very fragmented. There are a lot of islands, also a lot of smaller and larger rivers coming to the sea. And they affect the usability of model data because many of the operational circulation models of the sea operate at a much coarser resolution, something like 4 kilometers. I'm talking about those models whose data is publicly available. And of course, Earth observation can look into the smaller base, and especially these two, when merged together, they have potential to give new insights into the areas. But I promised to come back to the acronyms, and this might be familiar information for many of you, but everyone knows the Copernicus satellites or the Sentinels, the European heritage satellite missions, but Copernicus also has these thematic areas where they provide platforms, map interfaces, data sets, including validated data, even in situ observations and so on. And they are the Copernicus services. CMEMS is the marine use case related or marine oriented service. And there's a lot of data under these themes. models, EO, and so on. And especially speaking as a public administration person, a lot of the data is useful or is potentially useful, but there are quite limited opportunities to investigate what their accuracy actually is on a national scale or when compared against national information products or national databases. But there is a funding mechanism within the Copernicus called NCP, short for National Collaboration Program, and it means that a member state with its own projects funded by Copernicus, they try to create new use cases, validate existing Copernicus data, and make some kind of synergy between what the European level provides and what is available nationally. And there was a call last year where we applied and ultimately got this project. There is also another existing NCP project in Finland. It's Drifteri by Finnish Meteorological Institute. And then our coastal nutrients is the second in line. And both of these projects are active at this moment of speaking. But the last year's call, it was in February and March. They wanted to focus specifically on coastal monitoring. And the point there was that you either have an existing coastal monitoring service, or you are going to build a new service, or you are going to train the use of existing services. So your activities had to fall in one of these three categories. And Copernicus products also, they had quite a strict list of how you were supposed to use the CMEMS data. So either you improve the resolution of the marine model on the coastal areas, or you do some kind of machine learning, advanced data analysis, and so on. Or you could also validate the existing Copernicus data that are available, or do multi-source data integration. And our project falls within the last two on this. And we luckily had already an existing coastal service. I forgot to mention that we also aim to link our project with the FMI's ongoing parallel project. So we have an existing coastal service, which is called Takka, and Hanna Alasalmi had a nice presentation this morning about this service. If you missed it, Syke has a booth on the second floor, and you can also come there and get familiar with the service. But it's publicly available. It has served users almost for 10 years. I think we are going to have a 10-year anniversary next year. And the new generation of the service has a much improved user interface and many more data sets than the previous one. It has extra features when you log in and so on. Also a whole statistical analysis workbench. And in the new design, we have these themes where we can arrange the existing data sets underneath and then serve users in a much better way. And we decided to limit our NCP to these two areas, Archipelago Sea and Gulf of Finland. And I remind that we are mainly talking about the Finnish side of these sea areas. As many of you know, especially the Finns, but also people from other countries around the Baltic Sea, the sad story is quite similar in all areas of the Baltic Sea, but especially these two. The Gulf of Finland is rated as the poorest sea in terms of environmental health in the latest Finnish national assessment of the status of the seas. And Archipelago Sea also suffers from high nutrient inputs because there's a lot of agriculture on the catchments, and it's also listed as one of the hotspot areas in the Marine Protection Commission HELCOM's list, and it has been on the list for more than 30 years by now, and it's also included as a priority area in Petteri Orpo's governmental program. And there are also some activities focused on reducing nutrient input from there. But that's the geographical scope. And now I will be coming back to the project itself. So one requirement was that we offer 2 demonstration cases where the CMEMS data are sort of put together with something that you already have nationally, and you put them under the Takka service. And for demo case 1, we chose coastal total phosphorus, and there we plan to merge together the modeled phosphorus with our national EO-based product. I will come back to that soon. That activity has mostly been completed, and we are in the middle of collecting feedback for that. And demo case 2 relates to chlorophyll A, which has started the work, and we are expecting results by midsummer. So I will not be telling you much about that. The relevance of use case 1 and why total phosphorus is actually quite difficult to grasp with Earth observation is that there are basically 2 types of phosphorus in the sea. There's visible and invisible. And the invisible phosphorus, you see the molecule over there, it doesn't change the overall color of the water. So that's invisible to the satellites. It doesn't cause backscattering and so on. But then there's the particulate phosphorus which makes the water turbid. And with EO methods, we can only reach the other part of the 2, but with modeling, we can complete the missing part. And by merging these 2 sources, our goal was to make an assimilated or merged total phosphorus product, which would be valid from the estuary up to the open sea area. So the assimilation process was so that the Syke has already for several years made these downstream products of total phosphorus, starting from the turbidity product, which is available at the daily level. So there's a regression equation that converts turbidity into TP. And then Copernicus Marine Service, they have model-based phosphate. Notice they don't have total phosphorus. Phosphate is the model field. But we made also a regression equation to convert that to TP using all the data that we have. And we have all the data because Syke maintains the environmental databases of Finland. So we sit on top of all the data that we could use for this. And the merged product, the merging tactic is actually, it's a bit dumb. You start with the other product and then you smoothly transition to the other product once you go further from the river mouths. But it works, and I think the best thing about this is that it retains the features from both products. So you see things on the open sea and you see things on the coast, and that's what matters to the end user, to be able to actually make inferences of such large sea areas. And I will guide you through this example product from April 2023. It's right after the snowmelt period. So the Finnish coast has these, especially the estuaries, where snowmelt waters have flushed phosphorus from soils. And these are turbid, and they also have elevated phosphorus levels. But then on the Estonian coast, you see that there's some kind of thing being pushed towards or advected towards the open sea, and that I think is an upwelling structure, so it brings the deep phosphorus from deeper layers and transports it to the open sea. And that's of course because it has been there for the winter, it has mineralized, and it's very available to algae also to feed the upcoming algae production in the summer. So it's relevant for the users to know that, okay, now there's more nutrients coming from this side. Those who are the most accurate of you or have the most accurate pair of eyes can also see that there are these wiggles on this side. It's because this side of the sea is basically the model product. So it reflects all the same things that are given by the model output, and these are actually numerical instability artifacts of the model. I'm not going to talk too much about use case 2 since we just started the work, but the rationale here is that actually Takka doesn't currently have chlorophyll maps. And after this use case, it will have at least some kind of data assimilating both our chlorophyll statistics and the CMEMS high resolution, in this case 100-meter chlorophyll. And the main reason why we don't yet have the chlorophyll as maps is the high noise in the products, which can limit the usability. But our aim here is to do multi-source data integration to help create also products that are beautiful to the user. which of course creates credibility or adds credibility to the data. As a summary, or actually more like a point of advertisement, the total phosphorus use case is already published. There's this kind of sheet, product brochure on the Siemens website. You can already go there and have a look at it. The data are on the API, and we are soon starting also the consultation for feedback for these. But it's, as I said in the beginning, this is one of the rare opportunities to validate Siemens products because there's limited national funding, of course, for this kind of activities, but it's very crucial to be able to validate the European level state of the art, because if the products are good enough, they can be used for environmental monitoring and reporting as one key data source. This concludes all that I had in mind. I'm happy to take questions.
So, any questions for Sakari? Not at the moment, but yes, I could ask, did you have something special in mind in collaboration with the other NCP project? I think driftery is related to drifting models and some work related to that. Did you have something special?
And now, as a disclaimer, Jenny is the project head. So she knows what questions to ask. But I was also thinking about the same thing, and maybe that's something that the consultation round for the first product, or maybe the driftery is more associated with the second use case, the chlorophyll. So maybe that will come clear this spring as well. But we are happy to collaborate also because it was in our plan to do a collaboration with driftery.
Any other questions? If not, we are a bit ahead of our time because Krista Alikas's presentation was cancelled at a late stage. So perhaps we move on to Eero Alkio's presentation, which is about United Nations SDG indicator, also related to water quality. Just a minute. So this is about integration of satellite observations, Sentinel-2 to SDG eutrophication indicators in Finnish coastal and lake water areas.
Yes, thank you, Jenny, for the introduction. I'm Eero Alkio. I'm researcher at Finnish Environment Institute Syke, and as Jenny instructed, I'm going to talk today about the integration of satellite observations, especially Sentinel-2 data, to Sustainable Development Goal eutrophication indicators in Finnish coastal waters, and a little bit about the lake areas as well, if we have time. So about the Sustainable Development Goals, Syke reports to 26 of these indicators under four different goals, 6, 11, 14, and 15, and 2 of these goals are related to water quality. Number 6, the clean water and sanitation, and the indicator we are discussing today a little bit is the proportion of bodies of water of ambient good water quality. And then the second one is life below water, and our indicator is the index of coastal eutrophication. And first of all, so we have a lot of different reporting applications and commitments, and we want to harmonize our work, so we are not going to do it again. So we want to utilize our data in the sense as we are doing with the other European reporting applications like Water Framework Directive, Nitrate Directive, the Marine Strategy Framework Directive, and the Baltic Sea Action Plan. And the eutrophication is assessed in all of these different directives. And our focus lies in the chlorophyll A concentration. It's one of the national indicators proposed by the UN guidance for this index of eutrophication. And the chlorophyll A is a central indicator of eutrophication, both under these 2 directives that I discussed. And the chlorophyll A concentration is an estimation of phytoplankton biomass. And the phytoplankton biomass is directly It increases as a direct effect of eutrophication and is generally in the worst state of the indicators available. And it was chosen as Finland's first indicator now during this work. And previously, Finland has reported this indicator based on water sample data. And now we have evaluated about adding Sentinel-2 data to the indicator to complement the data that is, well, you know, water samples is not always sufficient data source. And the Finnish Environment Institute has a vast experience of using Earth observation data in water monitoring from 2003. And the Sentinel-2 data is already used in Finland, in the Finnish Environment Institute. So we are using the Syke's own recently updated and validated Sentinel-2 chlorophyll A datasets. And the chlorophyll A interpretation that we use in Syke is based upon a neural network-based atmospheric correction and biooptical model, Case 2 Extreme by Brockman Consulting. And then why do we want to actually add this satellite data to the indicator in the first place? What we expected that it would be the benefits is that it would improve the spatial and temporal coverage of the indicator and hence improve the confidence of our indicator. It should also harmonize the different assessments that we have to report under now. The base structure of our work is to first validate all the data from the water sample. So we analyze the matches of water samples and satellite observations. We have data in different categories. So we have data from designated monitoring stations and then on water body level. And that acts as the base unit of our work. And then we will aggregate these data sets to Finnish coastal water types and finally to the whole coastal waters of Finland. And here we have a data visualization example from our Takka service. So this is a data from 3 designated monitoring stations, one of them in the Gulf of Finland, Outer Archipelago, one of them in Åland, Outer Archipelago, and one in the Quark. And here the blue lines are the satellite observations and the red circles are the water samples. As we can see, the match is actually quite good, but of course these are now pre-selected examples. So in real case, it's not always this good, but this is the base that we're working with. And here the data we have is from the coastal assessment period in 2023, from 1st of July to the 7th of September. And when moving to the next level, so this is now a bit larger area, a water body level area. The correspondence is generally really good in water body level, but usually the Earth observation data, remember it's always Sentinel-2 data in this presentation, is giving a slightly lower concentrations than the water sample data that we will actually see in the end. And chlorophyll A water sampling data was available from about 200 of these Finnish coastal water bodies, but the satellite data was available from almost all of these. Only 3 were missing because of difficult or default special characteristics that we are going to discuss sooner. And then to the actual work that was done. So we had to now develop a method. How can we combine this water sample data with the satellite data? We decided to split the process into 2 different parts. So we are going to use 2 different weighting methods to analyze how we want to use the data and how much weight do we want to put to that data type. So the first method was temporal weighting. So we were analyzing how much data we actually have available of the water samples and Earth observation or with the satellite data. So we have about 20,000 satellite observations during this 6-7 years period and about 10,000 water samples from all of our designated monitoring stations. And the weighting method is described here, but maybe let's not go into the detail of that. But then to a little bit trickier part. So we had to also give a spatial weight. So we had to analyze where is the data coming from. So here we have a example water body map from the Finnish, I think this is on the Gulf of Finland outer archipelago area next to Hanko. And we had to decide what kind of spatial weights we want to give. And first of all, we decided that the water body must have at least 4 designated monitoring stations that are the red circles on the map. So in this case, in this water body, you can see we have quite many of them. So in total, I think it was 12. But how are they located? They are not representing the whole of the water body, in my opinion. They are clustered on a couple of key locations on the northern part of the water body. So we decided to add also a skewerness factor onto this spatial weighting method. So in this case, we are not getting any data on the water samples from the southern part of the water body. So we are not going to give the water samples a whole weight. And instead, when we are watching about what satellite data is actually giving us, so this blue area is the area that can be potentially covered with one satellite observation. It's almost covering the whole water body area, but on one satellite observation, we are not typically getting the whole area covered. We are maybe getting half, but when we get a lot of observations in our assessment period, we can assume that the whole area will get covered. It's quite clear. But the satellite data also has some constraints, so we can't get a reliable signal from shallow areas or areas that are covered with water vegetation. So we have excluded those areas from our statistics area, and these areas can be seen on this map as yellow areas. And we have this kind of analysis made to all of the Finnish coastal water bodies and also all of the lakes. And this is a work that had to be done manually. So we had to analyze what kind of reliability we can get on the satellite observations and with the water samples. And then we calculated the weights. So we have a temporal weighting. It's based on the days of data we have available. And then the spatial characteristics of a water body. And we took an average of these two. So let's get to the results. So we found out that we have we are happy with the quality of our data, and we have developed this method how we are going to combine the two data types. And then previously we talked about water body level. So then we had to actually aggregate these to finish water type level. So it's a larger spatial scale area. And these are now the aggregates of the water bodies. And almost all of these water types, the Sentinel-2 data gave actually a lower chlorophyll A concentration related to the water sample data. There are only 2 outliers. It was in the Bothnian Bay and Quark outer archipelago area where the satellite data actually gave higher concentrations of chlorophyll A concentration. But then we went further and aggregated these to the coastal level, which is actually the indicator that we are going to report later on. And as you can see, my bad. The weighted average now, it goes obviously in between of the in situ and Sentinel-2 values. But since we have a lot more of Sentinel-2 observations than the water body samples, the actual indicator value is going to be closer to the Sentinel-2 value than the water sample value. And about quick discussion or conclusion. So we implemented a method to integrate satellite data to water sample data, and we found out that it's actually working very well, and it can and should be included in this kind of indicator calculation for eutrophication index, but we think this could be also be implemented in other indicators as well. And it has, in this project, this was one of the indicators we were working on, but we also had some other indicators that we used satellite data with. And about what this did, so we expected that it would improve the spatial and temporal coverage and confidence, and it actually did exactly that, so we are very happy with that result. And generally, adding the Sentinel-2 data to the water sampling data resulted in a little bit lower chlorophyll A concentration, so meaning that Finnish coastal waters are in a little bit better condition than we previously reported. And with these weighting methods that we developed, it ended up that the satellite data will get a little higher weight than the water sample data, which we think is okay to go forward with. But there is still one thing we need to do. So we have to include the open sea areas to our indicator. Now it's only about the coastal waters. And we can do this, for example, with some HELCOM data that is, or HELCOM indicator that is using similar data that we are using now. So it's already using satellite data, water sample data, and flow-through data. And then this was now one of the indicators discussed. So this was about the coastal areas. Then we have another indicator that is now related to lakes in Finland, and it's much more complex because we have so many lakes and the reporting obligations in Finland. I think let's go briefly to that. So we have almost 5,000 lakes that we have to report under, and then we actually went with similar approach than with the coastal data, but this is not yet finished. So we accepted the chlorophyll A data on lakes from almost 4,000 of those Finnish lakes, and water sampling data was available from about 2,000 of these Finnish lakes. And then we classified these lakes on ecological status based on the chlorophyll on the satellite observations and water samples. And as it did go with the coastal areas, we ended up with a better ecological status in some of the water bodies, and also we had a lot more observations on the Earth observation data. But this is an ongoing work because we have so many lakes, and quite many of them are quite difficult to access. They are remote lakes in Lapland, and we don't have actually any in situ data on those, and we have to analyze similar kind of lakes and the data that we have on those lakes. But this is an ongoing work, I think, and we can discuss it later on. I think that was all. Thanks.
Okay, Eero, thank you for your presentation. It was really on a very hot topic because SDG indicators and the use of satellite observations on these, it's really done a lot throughout the world, and so the results and the indicators are pretty, the interest is high on these two indicators. So any questions from the audience, comments?
Thank you. Thank you for the great presentation, first of all. Very interesting. And this might be a hard question, but have you thought about trusting the relative shape of the chlorophyll A estimates of the satellite more, and the absolute values of the in situ more? Because from my understanding, the in situ measurements should be much more reliable in absolute values, but they don't have as good gradient as you see for the satellite data that has a better coverage. So for me, it might make sense to, rather than trusting the satellite more than the in situ, use the satellite to get better coverage, but then use the in situ's absolute values to adjust the possible errors in the satellite's chlorophyll measurements, since the atmospheric correction likely still has some some problems, even though the atmosphere is corrected.
Okay, thanks for the question.
Yeah, good question. So we are using the in situ samples to validate our data always. So that's the background. But now the work actually here was we wanted to analyze what kind of weights we want to give to this kind of data. Do we want to, because in situ is usually more reliable, but then we have this kind of limitations that it's not covering the whole area. So we wanted to analyze what is the optimal method to actually combine these and should we now give more weight to the in situ data or to the satellite data? And on smaller scale, like on this water body level, some of these water bodies we did probably give higher weight to the in situ data, but when we are watching or discussing the majority of these areas, then the satellite data tended to give more accurate information. But it's an important topic and very difficult to decide how we can choose the optimal way to combine this kind of data.
Okay, any other questions or comments from the audience? I think you raise a very good point in highlighting the importance of in situ data, but it's not, from my point of view, it's not always like in situ is better observation or more precise, because it also has a lot of variation depending on what time of the day you make the measurements and how accurate is the processing, and there are also lots of problems in laboratory analysis accuracies. So in a sense, they do represent quite similar accuracies if both measurements and observations are done in optimal way. But as you said, atmospheric correction is one of the things that can create problems, and lots of other issues also. Okay, if there are no other questions or comments, I think we will close this session and give Eero final applause. And then many thanks for this session. I can see that this was a very popular in comparison to the size of the room. So we probably all need some coffee now, and there should be coffee available.
Thank you.
Okay, so good afternoon everybody and welcome to the atmospheric session. My name is Anu-Maija Sundström. I work at the Finnish Meteorological Institute and I will be chairing this session. And I think we are ready to go. So the first talk today will be given by Sofia Järvinen from Finnish Met Institute also, and she will talk about monitoring NOx emissions.
Yes, thank you, Anu-Maija. Hello everyone, welcome to this session. I'm Sofia Järvinen from the Finnish Meteorological Institute, and I will tell you about how we can monitor NOx emissions from cement plants in specifically Nigeria and Egypt. We did this work together with Jolanda Jolongo and Janne Hakkarainen. Firstly, a little bit of motivation. So why do we want to study NOx emissions from cement plants? So cement plants are known to be major industrial sources of NOx, so NO and NO2 in the atmosphere. And the issue is that local emissions are often not well reported in specific areas at the company and national level. We thus can use satellite data to get global daily observations of NOx sources, and NOx or NO2, for example, stays pretty close to the sources, so we can use it as a proxy to also identify these sources. Here we have a picture from Tropomi NO2 on the left. Then where do these emissions come from in the cement production process? On the right we have this figure which, without going too much into detail, is just showing mainly the colors, the areas where these different types of emissions are coming from in the process. So firstly we have the thermal NOx, and also the most important type of NOx emission. And this happens in the rotary kiln in the red area in very, very high temperatures, so 14 to 1500 degrees Celsius. Then we have the fuel NOx, so from fuel in the nitrogen compounds in the yellow area here, and this is the secondary source of NOx in this process. Finally, we have the feeding NOx, so this is from nitrogen compounds in the raw materials, and a quite minor source compared to these top two here. Then our two satellites that we're using in this project. So we have the Tropomi, which many of you are familiar with, aboard the Copernicus Sentinel-5 precursor satellite. From here we use the tropospheric NO2 vertical columns. And we apply the advection divergence approach, which I will talk to you about in a little bit. Then we use the VIIRS aboard the NASA NanoAA Suomi National Polar Orbiting Partnership Suomi NPP satellite. And here we can look at the thermal anomaly detection. So these are also used to detect fires, but in this case industrial high heat processes. What's interesting about these two is that they have a very similar overpass time of about 1:30 p.m. So they're very suited to be analyzed together. Very quickly about this emission observatory website. So we have, this is like a project or data portal which is freely available to everyone, where we have cases in Africa of this different sector emission sources or hotspots. And eventually we will add the results from this study also to this emission observatory website. Focusing on 12 cement plant sites in Nigeria and Egypt. Nigeria and Egypt are both very prominent in the cement industry. In the scale of Africa, they're among the biggest, if not the biggest, producers of cement. We took these 12 sites based on these following criteria. So they have a large enough and distinguishable enough NOx emissions, and also they're away from other sources, as well as have some comparison data in the form of company or plant level emission information, essentially production or capacity information to be compared to. Then very quickly about the emission estimation method. Here we have an example of Gena site in 2019. So we are looking at the flux first, so including the wind vectors times the Tropomi NO2 vertical column density. Taking the divergence of this flux, we get two terms. The first is then defined as advection, and this is found to kind of estimate or indicate the local NOx emission sources, and then we take the emission estimation is then this added to the sink term. Then we get the estimation by integrating this data, so performing this fit to the emission data on the right end. What's significant about the estimation method is that it's not very absolutely accurate, or it has very high uncertainties, up to 30 to 40%. But for this reason, we are using it mainly as for trend analysis, so between different years and different sites in these two different countries. This Sinai site is one of our biggest sites that we looked at, and it has three very close together factories that El Arish cement factory is the largest one on the right, and then we have two very close by Sinai different company plants here. And these were together looked at as one source. As you can soon see, they show up as one emission source in our method. Here you can see that we essentially get this quite universal or maybe like one source looking data from this site, and El Arish is centered on the right here within these emissions. And we do the fit. Here's an example of 2022, and we found a comparison value of about 20% lower to our, or higher than our value, which is just a sanity check at this point that we are in the right ranges in this method. But of course, it's very hard to find specific comparison values for these estimations. We can see the trend here is obviously increasing. We also are including the COVID-19 years, 2019, 2020 especially. And then there are likely other factors, including maybe economic factors and overall cement industry factors that can contribute to this increase in emissions. Looking at all the sites, we then see comparing to the site capacity and site production. We see that there's a correlation of the emission estimations with these capacity and production. What's notable here is that we have these two very big cement plants. Here in red we have Egypt sites, and in green we have Nigeria sites. So in Egypt we have the Beni Suef and Sinai sites, which are dominating this red figure here, but also in the lower or smaller sites in Egypt, we see that there's higher specific NOx or NOx emissions per capacity and production in Egypt compared to Nigeria. We also compared to these thermal anomalies, and we see here as well that there's a correlation. Here on the left we have some example cases of emissions in blue and anomalies in red. And then on the right we have multiple sites correlations, which seem to agree to each other quite well as well. And this was done by Yolanda Yalanga as well. To conclude, the satellite observations can be used to estimate cement plant emissions globally. We looked at TRPOMI NO2 data and VIIRS thermal anomaly data together. And these annual NOx emissions correlate well with capacity production and thermal anomalies in Nigeria and Egypt. And we see this higher NOx emissions per unit of cement production and capacity in Egypt compared to Nigeria. We also see that thermal anomalies can be linked to or indicative of these cement production activities. We will hopefully add these emissions to the Emission Observatory website, and to expand on this work, of course, look at even more areas. In the future, the cement industry is definitely expected to grow even more, even globally. It's very an important sector. And also we could look at different satellite observations. So for example, CO2, or then later we will hear from Janne about methane observations using a similar method. Thank you very much.
Thank you very much. Excellent talk. So now it's time for questions, and since this event is streamed in YouTube, so whoever wants to ask something, so you need to use the mic. If there are no questions from the audience, I will use the opportunity to ask. So, what do you think, like, about some uncertainties? So, have you, for example, the wind data that you need for your emission estimation? So, where do you get that from? Is it model?
I'm actually not quite sure, but like what I do know is that it's quite difficult to get the correct information locally when estimation, and that's one of the main reasons why the uncertainties can be quite high. I don't remember at the top of my head.
Okay, thank you. But anyway, like the emission estimations went quite well with the inline, so that's good. Yeah. Any more questions? Yes.
Hi, nice talk. I was wondering, I'm sorry if I missed this in the beginning, what is your motivation? Since you had the ground truth and you show that it agrees, so are you going towards implementing the method elsewhere where you don't have this information? Do you want to validate the satellite observation? Yeah, I'm just curious.
Right. So in here we didn't have the ground data comparison, or we had the production data that we got from these sites. Yes. Where this could be used, obviously, maybe in this emission observatory website, we could use more cases there always. But I guess the main thing is just to kind of see and figure out different ways to kind of quantify and identify these cement plant emissions, because those are very not well available from very specific sites. So it's just kind of validating that aspect of the satellite observations.
Okay, thank you. Maybe we thank Sofia once more. And now it's time to move a little bit upper in the atmosphere. So we have Monika Selak from Finnish Met Institute talking about ozone and temperature trends in the mesosphere.
Thank you very much. Hello, everybody. So we are going higher up now. What I am going to talk today is about our recent project, which ended last year. At the end, it was ESA project, and it was the main outcome of the project was to create the mesospheric temperature and ozone climate data record. So the motivation behind this project was that despite the mesospheric ozone is very important for atmospheric chemistry, dynamics, energy balance, and understanding the coupling with the other layers, till now we don't have high quality merged data set of vertical ozone profiles in the mesosphere. And the ozone trends in the mesosphere, lower thermosphere region are very underexplored. As for temperature, here we have more data sets as well as more studies, but the majority of the analysis temperature trend, for example, is based on SABRE. So it's very good to have additional data set which simply for validate the results. So Meteor project objectives was to develop the procedure for merging, as we have strong diurnal variation in the mesosphere. Then creating the climate data record, of course, demonstrating the application. In our case, it was trend analysis, and providing the data sets to the atmospheric community. So the data sets we selected, there are six satellite instruments which cover the mesosphere in lower thermosphere. All of them are providing the global coverage except SOFI, which covers the high latitudes, and the resolution of all of these instruments is around 3 to 7 kilometers. And as for the time coverage and the volume of the data, so obviously the instrument with the dense sampling MLS has the biggest data volume, and it covers the years from 2004 to 2000 till now. Then we have MIPAS, which also pretty good data volume, which operated from, it's actually operated from 2002, but we are using data from 2005 as the MIPAS has some break and recovered with different spectral and vertical resolution. We use also another viewing mode from MIPAS middle atmosphere and upper atmosphere, which covers the same period and the similar data volume. We use, of course, GOMOS satellite, which operated from 2002 to 2012. And we use 3 solar occultation instruments, which is HALOE from 91 to 2005. Then we have ACE-FTS and SOFI onboard AIM satellite. So the solar occultation instrument has the lowest data volume, and they measure around 15 sunset and sunrises per day. So first step in the merging the data, it was to calculate the monthly zonal means, and we did it for each illumination condition, which means in the case of MIPAS, MLS, and GOMOS, it was daytime and nighttime based on the solar zenith angle, and for solar occultation instrument was sunset and sunrise, and the requirement was at least 10 profiles, 10 measurements per month. Because our main instrument, which covers the biggest period of time and has dense sampling, is MLS, we use the pressure MLS native grid as a pressure. And we created the monthly zonal means in 10 latitudinal zones, covering anything from minus 80 degrees south to 80 degrees north. And of course, the altitude range is the instrument dependent. So here you have example comparison between 4 selected satellite instruments. So we have the winter time mean, and this is nighttime ozone. So you can, and it's from MLS, MIPAS, nominal mode, MIPAS, middle and upper atmosphere, and GOMOS. As you can see that they compare very well. We have the clear 3 distinctive features. We have the primary ozone maximum in the stratosphere up to about 11-12 parts per million volume. And then we have the secondary ozone maximum, which is clear in all instruments which measure up to around 100 kilometers. The secondary ozone maximum values are similar to those in the stratosphere. And of course, in the winter time, in the polar region, we have the tertiary ozone maximum, which is created around 70 to 72 kilometers of about 2 parts per million volume. So they are very comparable. The results are very comparable from all of them. And then our step 2 was to remove the seasonal cycle from the monthly zonal means. We deseasonalized data using the different periods for seasonalized cycles. So for GOMOS, MIPAS, MLS, we use overlapping period of 2005 to 2011. For Halo and SOFI, it was full operational period, and ACFTS 2005-2018. And here is the comparison between the seasonal cycle for ozone, example for ozone at night, comparison of seasonal cycle from the GOMOS, MIPAS, and MLS. So the left column is for lower mesosphere, so it's 50 to 60 kilometers, and then we have 80 to 90. So as you can see, there is relatively good agreement between all of them, particularly at higher altitudes. Of course, we see some biases and differences, as you can see, but it's we expect that according to the previous validation and intercomparison studies between the instruments. Our third step during merging was to, I told you that the mesospheric ozone has strong diurnal variation, but after this is analyzing the data, so deseasonalized anomalies are nearly the same. So you have here the example from MIPAS, daytime deseasonalized anomalies and nighttime. And so we decided to take the weighted mean of these two different illumination conditions for each instrument, and we call it pre-merge anomaly. And we did it for all instruments, so you can see here a different color indicates the different pre-merge anomaly from different instruments. And then having that, we took the median of this seasonalized anomaly of these pre-merge anomalies for all instruments except Halo and SOFI. Because Halo and SOFI had different seasonal cycle period, then we applied small offset, and then after that, when we aligned the Halo and SOFI to this median anomaly, we took the median of all pre-merge anomalies. And in this plot, you can see that final merge anomaly as these dark red dots. And another example of how these pre-merge anomalies look like. So this is the for ozone example for ozones, 60 to 70 degrees south. So they are all these vertical profiles of pre-merged anomaly from different instruments. So we have GOMOS, ACE, MLS, both MIPAS, Halo, and SOFI. So they agree pretty well. We have similar variability, and when you look at the bottommost panel, so this is our final merge anomaly. So definitely we have different period with different coverage. So we are limited, before 2004, we are limited to the Halo vertical resolution, and also the time resolution. Time resolution is it's having much more gaps. And in order to check if any of these instruments show some drift, we calculated deviation of all deseasonalized anomalies from the merge. So you can clearly see that they are quite similar. They are less, usually the highest deviation is at higher altitudes, but no clear drift or no big deviation from the merged anomaly is showing up. And now to the application. So as I mentioned at the beginning, we use this merged data set, the anomaly data set, for calculating the trends in the mesosphere and lower thermosphere. That was the assumption, but we did that for the stratosphere as well. So what you can see here is two examples. So as we are limited to different, as we have different vertical resolution, depending if we are going to year 91 or we starting from 2004, we have different vertical resolution. So if we if we do trends analysis starting from 91, so taking all data sets, then of course we are limited by Halo, so we can we have trends from about 37 kilometers. When we do our trends analysis from year 2004, when we have best coverage, we can go down to about 22 kilometers. Those trends they are very similar to each other. So what you can see clearly here, we have as a sanity check, stratosphere is recovering. We have the positive trends in the stratosphere of about 1 to 2%, which is according to the previous assessment. So that was our sanity check of our data set. Then as for mesosphere, so mesosphere is cooling. So in the lower mesosphere, between about 50 to 80 kilometers, we have the negative trend, sorry, not cooling, we have negative ozone trend of about up to about 2%. Between 50 to 60 kilometers is completely not significant. And above 80 kilometers, the strong negative ozone trends are observed up to about 12% per decade. So we do not have much to compare with, but there is one study which was more than 10 years ago using the SABRE data. So Huang et al. Calculated the ozone trends using 10 years of SABRE data from 2002 to 2012. And they showed, the trends in the mesosphere were close to zero, completely not significant. There were some indication of negative trends, but they also showed that above 90 kilometers, then the ozone exhibit negative trends of about 10%. So a little bit similar, but of course this is more than 10 years ago and only using 10 years of data. As for temperature, so we use the same method, so multiple linear regression with standard proxy applied, and this is the results for this full period of time, so from 2004. And of course, predominantly we see negative trends, so stratosphere and mesosphere is cooling. The cooling trend is of about 0.5 to 2 Kelvin per decade. And we also see the positive trend in the troposphere. It's less than 0.5 Kelvin per decade. Here we have more possibilities to compare with. So one study using HALO and SABRE data from 1991 to 2020. This is the same region marked, so we are very close to what was already done. So they also showed that negative cooling of the stratosphere and mesosphere. And as for tropospheric region, so the study by Steiner using the radio occultation data from 1979 to 2018 also showed similar magnitude warming tropospheric trend as in our data set. So as a summary, we have now two matched data sets. One is for ozone, one is for temperature. So our primary goal was to include the 6 instruments, but for the temperature, we actually decided add additional 3. It is GOMOS Edge ATP, OMS LP, and OSIRIS. Sophie is there twice. The data sets covers the period from 1991 to 2023 with the 10-degree latitudinal bins, global coverage, almost global coverage, from around 22 kilometers to 100 kilometers. Uncertainties for ozones are less than 2% overall, but near the mesopause they go to 5 to 10%. For temperature, it's 0.3 Kelvin. At the mesopause, is up to 1 Kelvin. One thing I would like to add, together with this seasonalized anomalies, we also calculated provide the ozone in absolute values. We did that using the MLS and MIPAS seasonal cycle applied to the anomalies. So the full data set provided to the community not only has anomalies but also absolute values. And here are links to the data set and the preprint for the publication, which is evaluation of ozone trends in the mesosphere and lower thermosphere. Thank you very much.
Thank you. Very nice talk. So, do we have questions? If we yet... okay.
Thanks a lot, Monica. I have a question that are some modeling communities now going to use this long-term data set for improving modeling or something? Do you know if...
So this is another motivation which I didn't mention, that this data set would be useful for validation of model results, and particularly in the higher altitudes. But we have to distribute it and advertise our data set to be able, if they are going to use it, because for now it's just, even that data set is, I think, under reviewing, so it will be available in 10 days, but then we have to advertise the data set.
Any more questions? Then maybe I could ask one. So you have like pretty extensive time series now, like it's very impressive starting from the 90s. So do you have the future secured?
Yeah, that's the problem, because we have MLS, which we don't know what time there will be no MLS. Among all these data sets, we have still ongoing ACE FTS, and then we actually don't have anything. So until MLS is working, we can extend the data set and ACE. Of course, there is SABRE, but for a reason I mentioned, I didn't include it here, and also SABRE suffers from some drift in ozone measurements. So let's hope for the best for MLS.
Okay, thank you. And let's give one more. Thanks for Monika. And now we are going to the next talk, which is given by Evgeny Zubko from the University of Helsinki on aerosol microphysical properties.
Thank you. Thank you very much. I will be talking about improvement of our knowledge on reflectivity of aerosol particles. Aerosol particles are identified as the largest source of uncertainty for radiative forcing effect computations, estimations, and so in this way they affect energy budget on the Earth. We will consider how it could be reduced greatly by means of polarimetry. So I need to introduce you briefly into polarimetry, what it is. Basically, we refer to Stokes parameters, which are quite often organized into four-dimension Stokes vector, like it is shown here. The first element here is irradiance, and then three other, it is difference of two irradiances, measured with different orientation of polarizer or analyzer. Q is, this is just the one which is perpendicular, parallel to scattering plane minus perpendicular. Then you incline this reference system for 45 degree, and you get next cup pair, and then this is right minus left. This is already a circular polarization. What it gives us, if we organize scattered light characteristics in the Stokes vector, then we can actually describe light scattering act as a product of matrix 4 to 4 to the Stokes vector. It will yield you another Stokes vector, scattered light. This matrix is often referred in the literature as a Müller matrix, and it consists of 16 elements. But amazing thing is that in the most of circumstances, aerosol particles are well averaged over the orientation, our sample particles, and then this Müller matrix takes on quite simple shape, like it is shown here, block diagonal. And finally, because we work with polarimetry, this is very much passive remote sensing technique. And in passive remote sensing, we do not eliminate any radiation toward aerosol particles. We use sunlight that got scattered to us by these aerosol particles. An essential feature of sunlight is that it is unpolarized, which means its Stokes vector is like this. So when you multiply this to this, you will get only two non-zero values in the resulting Stokes vector. So they are referred, the upper one is referred as intensity or irradiance, and the second one we never consider alone. We take ratio of the second one over first one, And this is what constitutes degree of linear polarization. So this is basically, we had unpolarized light, we have scattered light that is already partially polarized. And the degree of linear polarization gives you a amount of light that got some polarization from the scattering part. And good thing that because of it is relative value, it doesn't depend on number of particles within field of view. It depends only on the light scattering properties. This is just figures that explain the same paradigm, but in terms of picture. So we have sun, we have aerosol particles, we have radiometer, which is equipped with analyzer, and these 3 points gives you scattering plane. Then 2 orientation of analyzer will give you 2 fluxes or irradiances, and you will get degree of linear polarization as a ratio of these 2 difference and sum of irradiances. As you can see, polarization can take negative and positive values. In this case, negative polarization means just that as a component of light that is vibrate within the scattering plane dominates over that one vibrating perpendicular to the scattering plane. Finally, phase angle. We refer to phase angle, it is astronomical tradition. It is just supplementary angle to the scattering angle. So when you sum up them, you get 180 degrees. So how degree of linear polarization of aerosol particles look like? This is just generic angular dependence. So we have negative polarization at small phase angles, and we have positive polarization at large phase angles. So minimum of negative polarization and maximum of positive are characterized with 2 numbers, the amplitude and location in terms of phase angle. And most of what we will be discussing corresponds to this one. It's really magic scene. I will show you in one slide. But first I would like to show how actual measurements look like for aerosol particles. So we do have negative polarization, and data more or less arranged along one side, one line, but at side scattering we do have huge dispersion of polarization maximum. And it has meaning in terms of reflectivity or reflectance of aerosol particles. This is very old result, which was formulated by Nikolai Umov 120 years ago. He was studying different samples, and what he found is inverse correlation between polarization. He didn't even say polarization maximum. He was measuring polarization of samples and the reflectivity, and he found that there is an inverse correlation. Later on, there is a significant contribution from French scientists, like astronomers, Dollfus, who did calibrated for the moon. And it takes some time before we realized how it quantitatively can be described, what kind of values should be substituted to this Umov law. But we ended up with this very simple interrelation. So we have maximum of polarization, and it inversely correlates with geometric albedo. Geometric albedo is just reflectivity by pi. Now single particles, how it looks like in practice. There are 2 types of particles here. We refer to them like agglomerated debris particles and some loose clusters. They actually reveal the same trend. So what is shown here, this is logarithm of maximum of polarization versus logarithm of geometric albedo. Very simple interrelation, and you see it is actually linear. Real part is fixed to 1.6 of refractive index, and imaginary part varies, and it is what makes this dependence. In the middle and on the right, this is power law size distribution with different values of the power index. Very simple. So if you know this diagram for aerosol particles in Earth's atmosphere, you measure the polarization maximum, and then you get the reflectivity at backscattering. So how to measure this in practice? Actually, the best condition is to measure this from orbit. Imagine that you have some satellite equipped with polarimeter. The best case if it is also equipped with LiDAR, but this is different requirement for size of satellite. So because of polarimeter, it is passive remote sensing technique. It means much smaller size and much less contribution of energy and mass. But LiDAR you can put on the ground. Then when this satellite passes our terminator, which is line that is where day changed to night or other way, it looks down. In this specific geometry, sunlight gets scattered from aerosol particles upward at phase angle or scattering angle that is really close to 90 degrees, where we have maximum polarization. So you do not need to change, but this geometry gives you additional profit. When you look down from the orbit, in this terminal, or on Earth, it corresponds to twilight time, when sun is already beneath horizon, so surface is already in shadow. But air above you is still highlighted by sunlight, so you can measure. So there is no contamination from the underlying terrain. You can address immediately to aerosol particles. No models are needed to discriminate signal from aerosol particles. And then, using polarimeter, you have maximum of polarization. Using Umov law, you retrieve from maximum of polarization, you retrieve reflectance. And then if you have LiDAR, this way or another, combined with your measurement, then you can get also number density or dust load. So you can get number of particles and the efficiency at scattering. So if you are not able to do that from orbit, you can do that from ground in twilight. So this is just what I was explaining before. And this is just concluding remarks. So polarimetry is an extremely powerful technique. It is passive remote sensing technique, yet it provides proxy to reflectance of aerosol particles by means of the Umov law. And if you measure this in twilight, you can address immediately to aerosol particles and hence have no contamination from the underlying terrain. This should greatly improve retrievals of radiative forcing effect from aerosol particles. Thank you for your attention.
Thank you, very interesting talk. So do we have questions from the audience? If not, so I could ask, so have you tested this with the real measurements? So do you have had the setup of satellite observations and real LiDAR and so that you have all these parameters?
It was done, but it was done separately. Still no immediate LiDAR in use simultaneously. The problem is that these measurements from ground, you can do it easily at astronomical observatory because you need to have all this frame. We tried it with very simple device, but because you don't know exact time, exact geometry, telescope, I mean astronomical telescope, is linked to all this necessary data for analysis. So at astronomical observatory, it is very easy to do without LiDAR, but if there is additional LiDAR, it could be done. Yeah, thank you.
Okay, thank you. So if we don't have any more questions, one more round of applause to Yevgeny, and then we can move to the next speaker, who will be Johnny Ase from the Norwegian Defence University College, talking about using AIS data to calculate the carbon footprint of Antarctic tourism.
Thank you. Yeah, thank you for the introduction. What I'm going to do is to go through a paper that I and colleagues from the Netherlands, Spain, and Argentina published last year. We were actually quite lucky. A Chinese group published a similar and excellent paper just 1 week after us. So I guess we were just plain lucky. So kudos to our Chinese colleagues. What we have been doing is looking at the carbon footprint from Antarctic tourism. Today, Antarctica is a high-end tourist destination, and the number of vessels and tourists that are coming to the frozen continent has been increasing quite a lot. We saw a dip in the numbers during the COVID years, obviously, but since the 90s, the number of tourists that have been visiting the Antarctica has been increasing 20-fold. The tourism industry is trying to sell this as those that are visiting Antarctica shall become what they call Antarctic ambassadors, and telling their friends how important it is to protect the Antarctic environment. What we found is that going to Antarctica is probably not the best thing you should do if you want to protect the environment. So the figure here shows the tourist traffic in the season 2022-2023 that we have been looking at. AIS, Automatic Identification System, is a system that provides data about voyage vessels. So what I plotted here is the voyages of 6 vessels around the Antarctic Peninsula. It's high. The data sets have a very high resolution, both with meter accuracy, spatially and temporarily, measured in seconds. So when a Zodiac is landing on a beach somewhere, I can find out, okay, where on the beach did it land, with an accuracy of just meters. Obviously, as we rely on satellites, we have gaps in the data sets when there are no satellites passing over. So for the first few years, we launched our first satellite in 2010. There are huge gaps in the data sets, but they have the quality is improving as the number of satellites are increasing. So this is a grossly simplification of the method that we used. But we were looking at the 2022-2023 season, which we estimated was between the 1st of October and the 15th of April. We were using the AIS data to reconstruct all 884 voyages that the different tourist vessels were doing. We were gathering engine specifications for each vessel or vessel class, and this was kind of cross-referenced with the several databases to verify and improve accuracy. The big challenge when you're doing this kind of test is that you have a data set, and you are able to calculate something, but you do not necessarily. But going from there to what you really are interested in is not always straightforward. So we have been using the propeller law, as was published in 2023, that the power of that's generated by vessel is a constant multiplied by the cube of the vessel, the velocity of the vessel. This we used to calculate the energy use for the entire trip in kilowatts. A paper from 2023 states that it takes about 175 grams of fuel to create one kilowatt hour And to get CO2 equivalent, then you multiply that number with 4.237. As I said, it's a gross oversimplification, but that's the main approach that we used. When we are looking at Antarctic tourism, then the voyages usually begins from 5 gateway cities, which Ushuaia in Argentina is the one that has most departures. Antarctic tourism comes in 6 different kinds. You have the traditional seaborne voyage to the Antarctic Peninsula, with landings where during the usually kind of 10 to 14 day long voyage, you visit several locations on the peninsula to see penguins and wildlife and historical sites. For the really big vessels, which have more than 500 passengers, they are not permitted to make landings. So they are just cruise only to sail in these waters, and they do not make any landings. There are also some vessels that sailing beyond the Antarctic Peninsula into the Ross Sea. And there are also some vessels or some tourists that fly from Argentina or Chile down to an airfield on King George Island, so you don't have to go through the Drake Passage. It saves you a few days with the usually pretty heavy seas. In addition, there are deep field expeditions into the Antarctic continent and yacht tourism. We have not been looking into those. So, when we're kind of looking at the total days of tourist vessels operations, we see that most were in December and January, and decreasing as we approach the beginning of the end of the season. What we see is that it's using a lot of fuel, where the traditional voyage to the peninsula uses a lot of fuel there, and also similar CO2 emissions. So our results, they were, as you see, that we put the per capita per trip, the emissions vary quite a lot among the vessels. You have some that are pretty new and using environmentally friendly fuel. They don't create that much emissions. On the other hand, you have some pretty old vessels that use more fuel. So the average per capita is also for some of these voyages is almost 25 tons, which brings me to the conclusion that Antarctic tourism is not environmentally friendly at all. These methods can also be used to do similar calculations up in the Arctic, where Greenland, Spitsbergen, and northern Canada, Alaska, are similar high-end tourist destinations. So as it is a high energy consumption activity, I think that the only thing that's worse is space tourism. There. So, thank you.
Thank you very much for an interesting talk. So, and we have a question. Great.
So, thank you very much. As I understand, you compute this carbon budget just for this cruise part. But I suspect that many of these people actually do not live in Chile or Argentina and come from the other part of the world. How is it on this scale? And also, one more small question. What would be an environmentally friendly tourism? Is there such a thing except for local tourism?
Yeah, thank you for two really good questions. In our paper, we also calculated the carbon offset for people flying from other parts of the world to these gateway cities. I didn't include it here in my paper, in my presentation, as we were just looking at AIS. But we see that the transporting a person from say North America or emerging markets to Argentina, the carbon offset is very, very high. So we did that as well, but I didn't include it here in this talk. Yes, it does. So it makes it even worse. So just think of someone flying from Norway to the Hurtigruten vessels sailing out of Ushuaia. It takes, there are two pretty long flights and produce quite a lot of carbon. Your second question. Sailing vessels. So you have one that's called Europa. It's a beautiful vessel. So, going old-fashioned with the sailing ships, that's the way to go. So I have some friends who are actually on the Europa now, and they are sending me some pretty good pictures. So. Obviously, there is no place like Finland, but you know, if I had the choice, I would be with them. That's my second choice.
Thank you. Do we have any more questions, or do we? If not so, then thanks for this interesting talk. And now it's time for the final talk of the session, which will be given Janne Hakkarainen from Finnish Med Institute, and he will talk about the persistent methane emissions.
Yeah, thank you very much, Anu-Maija, for the introduction. And yeah, it's my pleasure to give this talk and to say that this paper was just published today. So if you want, you can check it out also online now. But anyways, we will talk about persistent methane emissions from Secunda CTL synthetic fuel plant. Using S5P and GHG satellite observation. And this work in general is about our, or is related to our emission observatory project that Sofia already mentioned. And in general here we try to analyze different kind of anthropogenic hotspot emissions, especially related to this pilot project emissions in the continent of Africa, which definitely Secunda CTL is part of, as it's located in South Africa. So CTL comes from coal to liquids, so it means that they produce fuels from coal. And this site is operated by Sasol, and it was established in the 1950s. And expanded during the apartheid era to, for example, to avoid potential oil embargoes. So it's the single largest greenhouse gas source in the world, although it's missing in various emission inventories, including EDGAR. And before the study, its methane emissions have not yet been fully characterized using satellite observations, although some studies, including some of our own, have analyzed its CO2 and NOx emissions. And as you can imagine, this Secunda CTL is a very complex source with significant methane emission expected from various processes, including fugitive emission from coal gasification and other chemical processes, various leaks, and also sources like electricity generation. So in this study, we used two different kind of satellite observation. So Tropomi Sentinel-5B, which is a traditional Copernicus mission, as well as GHGSat, which is a private Canadian mission, so private company. And it's also a third-party mission, so we obtained the data through a ESA third-party mission project. But related to this study, I will only highlight one thing, that the scale of these instruments are quite different. So the spatial resolution of Tropomi is about, at nadir, is 7 kilometers times 5.5 kilometers, whereas GHGSat spatial resolution is substantially higher. So there we talk about 25 meters times 25 meters. So they are, so the spatial resolutions are quite different in kind, and I will show you some examples later. But one aspect of this work is to how to get emissions from concentration. So here's a little infographic illustrating this. So we have some plant, for example, Secunda CTL synthetic fuel plant. It emits different gases into the atmosphere. Then these gases get carried around with winds. Then there are some satellites like Tropomi and GHGSat that measure different kind of plumes. And then together with external wind information, like from ECMWF and others, we can combine these satellite images with wind information, and with very simple data-driven methods and mathematical formulation, we can calculate emissions and then do some emission analytics. Whether it's instantaneous, so analyze the emissions from individual plumes, or in some application we can, for example, use this divergence advection approach, where we calculate directly annual emissions. And yeah, here are some pictures from the paper. So Secunda CTL is located in South Africa. There's a Tropomi plume. Hope this works. No. Well, anyways, you can see the Tropomi plume in panel B. It's quite high, one aggregated plume. And on this very same day, 23rd of June, 2023, we have also the GHGSat plumes available. So there were Tropomi sees one big aggregated plume. With GHGSat on this day, we have 6 individual plumes right above this Secunda CTL. So the scales of these images are quite different. And in this panel D, we have a kind of annual average of advection field, methane and advection field. And from this advection field, we can actually calculate the annual emissions for this plant. And yeah, in this study, we identified 24 Tropomi methane plumes in 2023 and 27 in 2024, originating from this plant. And these plumes are so persistent that we can also analyze this source rate using this divergence advection approach as well. And for this study, we were granted 12 GHGSat archive targets covering this Secunda CTL through this ESA third-party project. And of these 12 targets, 11 of those included plume detection, which kind of further highlights that these emissions are very persistent. And these individual targets, GHG-SAT targets, included, depending on the targets, from 2 to 8 different plumes detected different parts of this facility. And in this paper, we applied various different methods for estimating the emissions using, for example, cross-sectional flux method, integrated mass enhancement method, as well as our very own linear integrated mass enhancement method, as well as this divergence advection approach for annual emissions. And here are kind of summary of our results. So these different colors shows Tropomi emission estimates with uncertainties for different days. And then this black solid line shows the annual advection estimates. And this SASOL also reports the values, so that dashed line there are the reported values from SASOL. And then these green markers indicate that 11 GHG-SAT summed emission estimates. So you can see that these GHG-SAT estimates are quite a bit lower than Tropomi, or about 1/3. So this is the same information as in previous slide, but with a table. So all in all, with Tropomi or S5P, we get emission estimates, regardless of method, about 20 tons per hour. So that's the source rate. And with GHG-SAT, we get, let's say, for the year 2023, about 6-7 tons per hour. And it so happens to be that the value reported by SASOL is right in between, so about 11 tons per hour. And well, you can see that the GHG-SAT is about 1/3 of Tropomi, and that was more or less expected, and also something that has been reported previously by other authors. But of course, one part of the explanation is that GHG-SAT might miss some part of the mass, as different days have different numbers of plumes, and we just simply calculate the emissions from individual plumes. But of course, there are other explanations as well. Yeah, so here are some examples from GHG-SAT. So these are quite a bit higher resolution than Tropomi, and you can see different days there are different number of plumes, and we simply calculate one emission value per one plume, and then we sum them up in the end. So if we go, here are 6 examples, here are 5. We can a little bit go back and forth between these pictures, so you can see that the location of the plumes a little bit changes from day to day. But overall, this kind of individual plumes are quite useful when we try to see which part of the plant is actually emitting methane into the atmosphere. But anyways, I come to the end of this presentation, but I hope you have learned that satellite observation can support emission monitoring, especially, well, here we have some information available from SASOL, but also in cases where there's no other information available. And in general, satellites can offer quite good independent audit tool for this kind of plants. And yeah, this is one part of our activities in this emission observatory project, and of course, we are very keen to collaborate with those who want to analyze these things further. And yeah, as I mentioned, this is one part of this work. So we highlight that with Tropomi data we get for the CTL plant about 20 tons per hour, but there are also many others. So you can go to Emission Observatory website to see some more. And of course, Sofia already in the first talk of this session highlighted these emissions from these cement factories. But yeah, with these words, if you have been, thank you for listening.
Very nice, thank you, Janne. And do we have questions?
Thanks, Janne. Just the question, if you would have in the same resolution as you had the GHG sat, now you had the methane there, but if you would have nitrogen dioxide, would you expect it to come from the same places or different places?
Well, it depends on the process. In general, no. So in this case, or actually quite often, methane and NOx, they are kind of co-located but not co-emitted, so they don't come from the same processes. So in this case, they would be different. Most often for CO2, they are like co-emitted, so they come from fossil fuel combustion, so CO2 and NOx in those kind of cases would be from the same location. Although that's not even generally true. For example, for cement factories, that's not true. And that's also not true for, I don't know, steel production and that kind of things. But when we talk about fossil fuel combustion, they come from the same sources.
Okay, any more questions? I might have one. So you showed like there were different methods used for the estimation, like estimates, emission estimates. So how should I, if I would like to here now draw one number for my report based on satellite observations, is there some kind of metrics, or how would you recommend that? Should always these emissions, for example, be retrieved with several methods and then take some kind of ensemble, or is there any kind of...
That's a very like fundamental question. There are like different methods work better for different kind of situations. So it's not always clear which one is the best. If I would need to recommend one, I would use cross-sectional flux method. That kind of is the, I would say, the gold standard. But that's not always the case. For example, for this very small scale, like GHG type of flumes, I would definitely recommend integrated mass enhancement methods for various reasons. But anyways, I mean, having them all and kind of analyzing them together might give you some insight. But in this case, if we take average of all of these, we get, I mean, it's 21, 18, 18, something like that. So if you take 20 and are happy with that, I would recommend using that number for here.
Good, thank you. If there are no additional questions from the audience, so we thank Janne and also all the other authors, and now we have the poster session upstairs.